Good afternoon and welcome to this second performance management workshop. My name is Pavle Vuletic and I'm the task leader of the work package 6 task 3 in the GÉANT project. This task is called monitoring and management. And in this workshop, our intention was to present some of the things that we are working in our task. You will see a couple of presentations, one from Raul and one from Ljubo, and I will show you the agenda soon. But also we wanted to hear what other people in the community are working in these areas, and we wanted to exchange information and to see where this whole field is going so that we can plan for our next steps. This is our agenda. Agenda is displayed at the Indigo page. The first session is related to high-speed network monitoring, and when we say high-speed network monitoring, we think about 100 gigabits per second and more. So you will hear three presentations. The first one from Raul, who did a lot of tests between the machines which are in GÉANT network in SURF and in RMP in Brazil. The second presentation is going to be a video. Unfortunately, since we have participants from different parts of the world, it is challenging to find the proper time slot so that everybody can join us. This time slot is slightly better for our participants and presenters from the United States. Unfortunately, for someone who is now in Australia, is around midnight. So this presentation from Andrew is going to be a video who he prepared and sent us yesterday, but Tim will also add a couple of slides and a bit of technical description in this second presentation. The third presentation is going to be from Richard Hughes-Jones about his experience and his results in 100 gig monitoring. Then we will have a brief Q&A session. This is a general remark. If you have any questions during the presentation or after the presentation, you can use chat. Please use chat and send the question. Maybe some of the questions can be answered while the other presentations are going. But if there is anything that we have to discuss a bit further and that cannot be answered easily in a chat, we will use this Q&A session at the end of each of this session to discuss this topic. Second session is about monitoring data analytics and correlation. This is something that we discuss a lot in the project. Basically, we want to understand what can we do with the data. We have some systems like the PMP system, and the first presentation is going to be from Ljubo, where we gather a lot of data from various measurement points scattered around Europe. And we have several years of history of these measurements. So we wanted to see how this can be used and what is the future of data analytics and how to use monitoring data in a smarter way than what we are doing right now, just displaying some graphs and understanding something from this, whether there is a possibility or potential to add some new features or some smart decision making. So this is something that we want to explore. The second presentation is also something coming from our work package from Fabio, detecting anomalous latency and jitter in Timemap, where Fabio is working with machine learning models and is analyzing the results that he gets in his Timemap system that is being developed within our work package. Then we will have a presentation from ESnet about AI/ML based path optimization. And this is going to be a second sub-segment within this session too. We will have a brief Q&A session between after these first three presentations, just to have to answer and to discuss the points that were raised in the first three presentations. Then we will have the last block of three presentations from our presenters from the United States, where we will hear more about SEND project, NetSage, and Stardust. So I hope this is going to be useful and informative for all of you, and for all of you who are listening this video, which is going to be recorded and placed on YouTube. We plan to finish this by 5 Central European time, around 5. So this means that we will have 3 hours of relatively intense discussions with 9 different presentations. And yeah, I hope this is going to be something that you will find useful. I will be a timekeeper, and I will warn all the presenters 2 minutes before the scheduled end of their talks, because we don't want this whole workshop to extend much more, much after 5 o'clock Central European time, especially because we have some participants coming from the Eastern time zones, which means that it is going to be much later than this 5 Central European time. As I said, feel free to ask any questions at any moment in chat. Of course, we will have those Q&A sessions at the end of each segment. Presenters, after you finish your presentation, of course, you can respond to these questions if you see them in chat. I think, this is a nice way. I mean, this is something that we noticed, that how people who participate in the workshop like to work and to ask questions. Maybe it's not always convenient to turn on the microphone and ask a question this way. So as you can see, this event is recorded. You will find it on YouTube in a couple of days after this workshop. I will send, I mean, through the Indico system, I will send you the link to the YouTube video, so you will be able to watch it if you missed some of the presentations. Unfortunately, this is this is the virtual event, so coffee machine is where you find your coffee machine during the coffee break. This is the second performance management workshop. The first one was in Zagreb 2 years ago, and it was the last event actually that we had where we participated in person in Zagreb. So I hope that this is the last event that we will organize this way online, and that some of the next workshops are going to be organized in person, and that we will be able to meet each other and to discuss by the real coffee machine and on a real coffee break. So I will now stop sharing, and I will invite Raul, who is our first presenter, to share his presentation and to start.
Hello.
Hello, Raul.
Hi, can you hear me?
Can you hear me? Yes. Well, loud and clear.
Yeah. Okay.
And we can see the presentation.
Yeah. First of all, I want to thank Duncan Run, because until yesterday, I didn't even know about this, that I should have used the template, GÉANT template. So Duncan rushed in the last half an hour to put the thing in the template, and he's going to pass the slide. He was very kind to accept that. So next slide, Duncan. So Duncan, I and Tim, we work with this WP6 package that Pavle leads. And more or less, we had a meeting with the people from Brazil, Marcos, Jefferson, and back in November, I think, and we agreed to run tests over the Bela link, which is there's a 100G link from Portugal to Fortaleza, and then from Fortaleza, it goes down to Salvador, São Paulo, other cities in Brazil. The idea was to isolate routing issues, tune personal hosts, test questions that come up every time about MTU, congestion window, what the tunings that can affect transfers. Try to find pacing so that we could run transfers with zero retransmissions, and try to drive a consistent TCP throughput of 80 gigabit per second through that link. We had initially 3 or 4 hosts in Europe. In the end, we restricted the test to Surf, to a host provided by Surf. Max from Surf was very kind to help me with that. And in this presentation, I'll restrict the results to tests from Surf to Fortaleza, because it is the first point in Brazil. Next slide, please. This is just to give you an idea of the path. When we started, I think we started early December, the first thing we noticed that there was a problem where the path from Surf and also from Imperial College to Brazil would sometimes flip from going through the GÉANT nodes to the GÉANT middle boxes to going through the US. I think, if I have a memory, that Duncan, even one day, he noticed the route through the US, from Imperial College through the US, was flipping, sometimes going through for IPv6 using one route, IPv4 another route. But now it is like that. This is our personal host, the personal host that Surf provided to the personal host in Fortaleza. Okay, just to give you an idea, the 9 hops, and that's 106 milliseconds. Okay, next slide, please. One of the questions, because we work with the WLCG 100G team, and Duncan work with them frequently. I started working with them recently. Also at CERN, Duncan and I work for WLCG. And from time to time, the question comes of whether it is worth to try to migrate all sites to MTU 9000. I had run a lot of tests. I even published a paper in CHEP 2 years ago showing the impact of MTU 9000 compared with 1500. We decided to do the same sort of test. The sort of test that we did here, we used the P-schedule option, this MSS setup 1500, because the 2 sites, both Surf and Brazil, have MTU at 9000. We were not testing whether ICMPv6 is correctly configured, among other things, because Surf is only IPv4. The Brazilian hosts were IPv4 and by IPv6 for some time. Then recently they are only on IPv4, so that was not the question involved. The question was whether MTU would make a difference. Increasing the MTU from 1500 to 9000 would make a difference at all. It's important to notice that I decided to, because I am restricted on time, I decided to show all plots that come from the Surf streaming telemetry system, which Max from Surf was very kind to make available for us. So every single plot that you are going to see comes from that system. Next slide, please. So this is one of the many tests that we ran from Surf to Fortaleza. I compared the impact of the MTU both on IPERF3 and IPERF2. On the left, the 2 first curves are IPERF3. On the right is IPERF2. As you can see, for each one of the pairs, the one on the left is 9000, the one on the right is 1500. As you can see, IPERF3 gives me 30 gigabit per second for 9000 MTU and less than 20 for 1500. Another thing that on IPERF3, on IPERF2, I get much better rates. This is a constant for all tests that I have. I can get much better rates from IPERF2 than IPERF3. There is one point that I saw frequently, unfortunately, that plot doesn't show very clearly, is that when you reduce the MTU to 1500, you add much more retransmits than when you are using 9000. Next slide, please. Another thing that we were using, I ran a lot of tests and published before about that, was trying to check the effect of the congestion window algorithm. Because the personal hosts involved all run on kernel 310, I think, and Red Hat CentOS 7, Red Hat Linux 7, the congestion algorithms were constrained to Rhino, HTTP, and Cubic. Previously, I ran tests, and it was in a talk that I gave at CERN 2 years ago. I also compared with BBR. In this case, I am showing a plot with, again, IPERF2, IPERF3, Rhino, HTCP cubic with 4 streams and a 64 megabyte socket length. As you can see, you don't see a real, you see that iPerf3 is much more performant, but you don't see a big difference in when you're taking, you are just comparing the algorithms. When I saw the real impact is when you start using MTU 9000 and you increase the socket length, and then there is a difference in the sort of throughput that you get from the different algorithms. Next slide, please. Another thing that I was testing was the use of parallel streams. A fact that people like Doug and I, we work for the WLCG. You never see a transfer between 2 sites that goes on 1 stream. Transfers usually go on 4, 8 streams, even 16 streams. Usually I see transfers to the site that I run, Brunel University in London, CMS transfers coming on 8 streams, 16 streams. Another thing is that transfers normally involve more than 1 site transfer. It is not one-to-one, but actually end-to-end sites transfer. It means that CMS, when they transfer data from Brunel or to Imperial College, they never submit a transfer for 1 file. It is always a data set that contains maybe 60 files, hundreds of files. And this affects the performance when you have MTU at 1500. So what we are trying to do here is to try to find out. I know that Persona tests hosts all over the world mostly are configured on 1 stream, but the fact is on real life transfers, it goes on more than 1 stream, and usually it is N site sending data to M sites. So the number is not always 1-to-1. This again, it shows already the impact if you have more streams. I am showing this just for HTCP. Well, there will be another slide comparing other algorithms. You'll see that when you increase the streams, iPerf2 on the right shows a nice increase, almost linear with the increase on the number of streams. iPerf3 also shows the same increase, but iPerf3 is not as performant as iPerf2. Next slide, please. I don't know if I'm rushing too much, but I'm worried that Pavle will cut me off in a minute. So I try to, and I have around
5 minutes.
Yeah, I think I can do it. But this shows transfer rates for 6 streams. Again, comparing the 2 tools and the free congestion algorithms. And this one, I increased the socket to 128 megabytes. Reno on iPerf3, Reno is the less performant, but I like very much. So from left to right, it is Reno, HTCP, and Cubic. The 3 on the right is iPerf2. The 3 on the left is iPerf3. Reno has this very nice that it shows less throughput, but usually the curve is flat at the top, and it shows tends to show very low number of retransmissions. I like that point very much. And in this one, you see already that we are getting close to 100G. I hope the Marcus in our RNP and Max in Surf, they will not be very angry with me because we had agreed that I would restrict the test to transfers of 5 minutes up to 80 gig. But I started getting enthusiastic, and once or twice I got to 90 plus. But I always restricted the transfers to 1 minute, and they were all performant performed overnight, like between 1 a.m. and 6 a.m. Okay. So next slide, please. This is again, just to compare, I moved from 6 streams to 8 streams to try to find some, if things could improve. You see that's hyper-free. There's a point where, at least I don't know, maybe someone will know the secret. I cannot get over 30 gigabit per second. 30 gig seems to be the limit. Okay. Again, it is, I'm comparing 6 streams is the first free curves. 8 streams is the next free curves. You'll see that on hyper-free, you get much higher performance, but the curves sometimes get very rugged, which indicates a lot of retransmissions. Due to restrictions of time, I collected the number of retransmissions, and you see the retransmission. It's always associated with this very seesaw curve at the top. Okay, next slide. Next slide, please. This is just to report some of the issues that we found when we started the work in December. We saw written issues from 2 RNP starting at Surf and Imperial College. Sometimes for a few days, the routing would flip from Belgrade to use the USA. This eventually was corrected by Max and GÉANT colleagues, I think in December. There was also some BGP issues affecting transfers to São Paulo and Salvador. They were corrected, I think, in early January. The present state is that I can transfer data on hyper-free, on doing up to 3 gigabit per second from Surf to Fortaleza, almost always without any retransmission. There is some asymmetry that I see for the same test when I invert destination, starting at Fortaleza to Surf. I see more retransmits than from Surf to Fortaleza. This is something we have to investigate. For a time, I even thought that the problem might be with the host at Surf. But then I started running some tests to Fortaleza from other sites in Europe, like KIT or CERN, and I noticed the same thing. There were against a high number of retransmits, a higher number from Fortaleza to Europe than from Europe to Fortaleza. I also noticed the same problem on transfers starting at Surf, going to US versus transfers at Surf, going to sites in Europe like Prague, KIT in Germany, CERN. I intended to have a plot about that, comparing the 2 cases, but in the end, things got a bit rushed in the last few days, and I couldn't finish it. Okay, next slide, please. This is just to show. This is the top that we achieved. This is hyper-2 transfers with 256 megabyte socket. It's 6 streams. Cubic and HTTP give a good performance. Cubic gave a performance. This was repeated several times of something. Peak performance 96 gigabit per second. I don't have averages in there, but I saw average like 92 gigabit per second with a very tight error bars indicating that it was really keeping 90 something gigabit per second. Those tests were all performed overnight. I tried never to run tests after 7 o'clock in the morning, 7:30 in the morning. This was an agreement I had with Surf to avoid tests in the commercial time, working time. Yeah. So this is the maximum performance that we achieved. Again, I repeated this several times and it worked very well. Next slide, please. This is just to give credit because in the end, I was just the guy writing scripts to run tests, collecting data, writing scripts to parse them, transforming in plots and things. The whole work was really done by GRNP team, Marcus, Jefferson, and the surf team, Max, also contributed to this work. Lots of discussions that we have every Friday at Jisc with David Richardson, who is our network engineer, Tim, and Duncan, who is always ready to discuss and to step in to put my presentation in a proper format. Thanks very much, Doug. Next slide, please. It is part of our task to produce a report covering not only the experiments to RNP, but to USA, Europe, and because all of these experiments I had run previously on a test bed in Jisc test bed that it has a Mellanox switch and 4 hosts connected with 2 NICs to 100G NICs. We ran several tests, memory to memory tests involving storage, tests aggregating the 2 NICs, and we got something like 190 gigabit per second with 2 aggregated NICs. Yeah, so we will have a report coming, hopefully not in a long way, maybe soon, hopefully in March. Yeah. Okay, any questions, please?
Thank you, Raul. So I suggest, as I said, that if there are any questions which can be put into the chat, that workshop participants do that, and we will have the Q&A session at the end. So I guess there will be some questions, and it will be also, I think, interesting to hear what Richard Hughes-Jones has been working with his tests and to compare the results that we got in our task and what he has done. In meantime, we will have this presentation from Andrew Howard about the DMC competition. So now I will share the video. Just let me do this. I hope this will play well. We tested this and it was good. I will ask just Ivana to confirm me, but not here in the workshop, but through the Viber, that everything goes well. So here is the next presentation. Just one remark. So once this report that Raul mentioned is ready, we will send through in the ecosystem and information to all of you, to all the workshop participants, that it is ready and where you can download it. So it will be publicly available. Now I will share this next presentation.
Hello everyone, I'm Andrew Howard, Chief Judge of the Data Mover Challenge and Associate Director of Cloud Services at the National Computational Infrastructure in Canberra, Australia. First of all, I'd like to thank Tim for inviting me to speak at this event. NCI is one of 2 Tier 1 HPC facilities in Australia. We are one of the largest data consumers on the planet, pulling in Sentinel, ERA, Landsat, and a number of other datasets continuously. We act as the Asian and Australia-Pacific regional hub for many of these datasets. Let me talk first about the rationale behind the Data Mover Challenge. We want to identify the next generation of data movement tools and capabilities able to effectively utilise 100 gig networks. We want to look at both academic and industry solutions. We want to build experience with both HPC storage and network tuning. But most importantly, we want to build a trust relationship between the current and next generation of NREN engineers and establish an ongoing relationship between them. We want to build trust between HPC facilities, and we want to establish a long-term 100 gigabit per second testbed capability operating over our production 100 gig NREN networks. We also want to gather a range of tools, containerized, able to be deployed on any facility in Kubernetes or in a virtual environment. So we want to build a curated tool set that we know we can rely and trust that has known performance capabilities. I constructed the data set, which is between around 1.9 terabits, consisting of both actual genome and satellite mixed data types and sizes. I constructed a number of mix of large and lots of small files. This is representative of a typical data working set for genome or climate analysis that we observe at NCI. We imposed a number of constraints as part of the Data Mover Challenge. We required the use of Singularity for containerization. We restricted access to remote DTNs from the public internet, requiring participants to jump through the NSCC Singapore system to access other DTNs. However, we did permit SSH tunneling. One of the major constraints was there was no root access to the DTNs, as these were capabilities owned by our partners. The judging panel evaluated any request for underlying operating system network stack related tuning, and in collaboration with our partners implemented those we considered appropriate. Each of the participants in the challenge were given 1 week to implement a solution and perform testing. The Data Mover Challenge network has continuously grown since its inception, with this year covering almost every continent on the planet except South America and Antarctica. We hope to continue to expand the range of the Data Mover Challenge network, connecting more and more Tier 1 and Tier 0 HPC facilities. Most importantly, this network spans the globe around 2 times and for the first time connects to the African continent through KAUST in Saudi Arabia. I'd like to thank our remote sites, NSCC in Singapore, CARNET in Australia, CSC in Finland, Starlight in the USA, KAUST in Saudi Arabia, KISTI in Korea, NICT in Japan, SURF and the University of Amsterdam in the Netherlands, and ICM in Poland. The DMC network implementation changed in a number of ways from previous iterations. In previous iterations, we had used an extended layer 2 VLAN configuration, which, extending it to the network extent that we had, proved extremely problematic. We experienced limited experience within the current generation of network engineers constructing extended VLAN overlay networks without the utilization of an overlaying orchestration system like Genie. This also provided poor visibility of the overall data flows, congestion, latency, and visibility to the participants operating in the challenge. We also uncovered issues with international routing, where inactive VLANs circuits would time out from the router ARP tables, creating difficult to troubleshoot scenarios. The solution to this is to run periodic pings to keep the network active with at least a baseline data flow. However, we pivoted to using standard layer 3 network access running over global production R&E networks. We want to engineer for ongoing 100 gig data flows and emerging additional networks which can have more than 100 gig data flows. We also want to observe and tune real data traffic flows. The participants had end-to-end visibility of the latency and congestion, and we wanted to identify and share best aspects of best router and switch tuning under real-world performance scenarios. And we also wanted to determine how fast these tools would work over our contemporary high-performance R&E networks. I'd like to thank all of our DMC21 supporting partners for their networks, their storage resources, their technical expertise, and their ongoing support and encouragement, and especially the UVA team, whose logo was accidentally omitted from this graphic. In total, there were 7 participants, 2 of which were eliminated early in the competition. leaving 5 ultimate competition winners. I'd like to announce Team Mushishimo from Japan, the most innovative and best IPv6 performance. Their solution produced a proprietary protocol operating alongside contemporary IP protocols, able to operate well over impaired and congested network conditions, and tuned to operate in a natural disaster situation in the Japanese context. Architecture was the most comprehensive, complete solution and best software architecture. Architecture's product, MediaFlux, is an integrated data management platform which has data replication capabilities and S3 object presentation, as well as a number of other protocol interfaces. Fast is Good received the award for Best Virtualization Support. Fast is Good were able to encapsulate their solution into containers most easily. Their solution focused on working through firewalls and other impaired network conditions to deliver video files for live video production and for editing services. Globus is a well-used application toolkit throughout our community and received the best integrated software experience. They were able to pivot their existing Globus service to operate easily within a container environment and produced an excellent software data transfer experience able to integrate into existing workflows. The overall winner, Team Sienna, ICAIR, and UETN, were the best long-distance performance and overall winner. Sienna, ICAIR, IETN produced an application stack which was integrated into a Jupyter notebook, which had machine learning capabilities, able to tune best network paths, to orchestrate underlying optical fiber operation and setup, to select the best protocol, and to also provide a graphical interface into a Jupyter Notebook workflow, which is able to be integrated into other Jupyter Notebook workflows. As such, our judging panel awarded them the best overall winner. Each of the participants had a unique solution and a unique approach to solving the problem, and we wish to encourage both a diversity and an overall capability for the Data Mover Challenge. We'll be conducting another round of the Data Mover Challenge in 2022-23 with announcement at Supercomputing Asia 23-24. If you'd like more information, please contact me at the email address below, or more preferably, I'd like to hand over to my colleague Tim Chown, who is also a member of our judging panel, and will be able to provide all technical details that you may wish to know of the nuances that I have not covered. Thank you very much, everyone, and I wish you a great conference. Good night.
Well, thanks to Andrew and his presentation. Now, Tim, Tim, you started to share your slides. Please describe a bit of technical details. And unmute your microphone.
Yeah, oh, sorry, Pavle. I'll learn how to use Zoom one day soon. Yeah, just a few slides to complement what Andrew said there. The thing to emphasize here is that the Data Mover Challenge Network is essentially there as a test bed to encourage both learning of best practice in configuring DTNs in the network, but also to encourage people who are developing software to do large-scale data transfers, to give them a real-world research and education environment in which that software can be tested. So what happens, as Andrew said, is each team gets access to this infrastructure for a week with the 9 DTNs that are available. They can play for the first few days, tweaking and tuning, maybe request tuning to the OS, and then they run their final test from which they get their results. And then there's a little judging chat with them at the end of the week. So we did this for all the teams. The tests are run that they're judged in terms of performance are run between specific combinations of DTN sites around the network that Andrew showed you. I'd like to emphasize that there's both IPv4 and IPv6 in that, but 2 of the team's software did not support IPv6. So while we're very keen to encourage people to enter again, as Andrew said in his last slide, it'd be great if all the teams could include IPv6 as well. In terms of the performance that was achieved, just to compare to what Raul reported in his talk, the winning team got performance from Amsterdam to Singapore of 85 gig memory to memory, and from Amsterdam to Australia of 84 gigs. So that's pretty impressive. A number of the other teams struggled to get much above 10 or 20 gig, but this application was well written, well tuned, used parallel flows efficiently, and did well. One thing I'd just quickly like to mention there is that the University of Amsterdam, their DTN was hosted behind a white box, an edge core wedge with multiple 100 gig interfaces running the rare free router platform that's being developed in the GÉANT GN4-3 project. So that does provide that, and the evidence of the results and the performance here shows that this fairly cheap white box, it's 6,000 or 7,000 euros, running this open platform can be a very performant platform. In terms of the DTNs, again, Andrew said we had the 9 organizations that provided them. It would be great if more organizations get on board for next year. There's obviously a gap in South America. RNP would be very welcome to get involved, I think. And obviously they're doing a lot of work with 100 gig testing. I've just listed some of the things here. These were the specs, broad specs that were given to the participant sites in terms of what they'd be expected to provide in terms of a DTN that would be used in the competition. And the organizers, Andrew and his team, then used Ansible as a means of doing the automation of configuring those devices. And the tuning was following, perhaps no surprise, ESnet's faster data guidance that you can find there and elsewhere on the faster data site. And then just my final slide here, this shows you the broad specs of the 3 machines that were involved, DTNs that were involved in those 85 gig throughput tests from Amsterdam to both Singapore and AARNet. So you can see the nature of the machines that are involved there. So these slides will be online, so you can have a look at those at your convenience. So that's all I just wanted to add, just a bit of technical grounding to Andrew's talk there. Thank you.
Thank you, Tim. So if you have any questions related to these 2 presentations, also put this into a chat. I saw also a message from Marco Schwartz from RNP that RNP is very interested in committing some of the resources used for the 100 gig tests. So yeah, we can discuss this in the Q&A session, or later take this offline. Now I would like to invite Hughes-Jones from GÉANT to share his screen and to start his presentation on achieving 100 gigabit performance.
So I also have trouble finding the unmute button, but thank you very much for inviting me to share the measurements we've made in achieving 100 gigabit performance end-to-end we're using TCP/IP. I will cover 3 broad areas: tests between end sites in the UK and Italy using Jisc, GÉANT and GARR, transfers between Latin America and Europe using the ELA submarine cable, very similar to what Raul showed earlier, and transfers between Australia and Europe using both paths by the US and the CAE link, which was fairly new recently. So starting with ECMWF, they wanted to create a new compute center in Bologna in Italy and move the data from Reading to Bologna. They'd already got 100 gigabit access links from Jisc and GARR, but they wanted a little bit of assistance to set up their systems, their sites, and to be able to move the data at the rates they wanted and make sure they understood what they were doing. It was a very, very good collaboration in terms of sharing information and knowledge. So we worked together to set up DMZ and also to tune their DTNs following the recommendations that we made in the Aeneas Horizon 2020 project. So they started with their two nodes in Reading. So we made tests which were like the baseline. Then as they moved one of the nodes to Italy, we tested to London and then to Paris. Now, one of the unfortunate problems is that the computer center wasn't ready on time. I think that's fairly common with many building things. So what we did is we asked our NOC to set up two different paths. You see the yellow one here is 16.1 milliseconds. It's a standard path, if you like, between the UK and France. But we also set up a much longer route of 38.4 milliseconds going via the Netherlands, Frankfurt, Geneva, back to Paris. And that was to emulate the total distance that we anticipated going to Bologna. So we made the usual tests of TCP throughput as a function of TCP buffer size, but I have got the time to show you all the details, but we then decided that we would make two long flows. So we used iPerf3 on two pairs of CPU cores after doing the tuning of the kernel parameters, the power settings, the MTU, the NIC ring buffers, and the interrupt locations, for example. And we allowed the flows to use what I've called TCP auto tuning. We didn't set the buffer size in iPerf3. So the single flow was stable around 30, 32. And we ran it for a total of 12 hours on the production network. And here, this graph shows you the sum of both being about 60. And you can see that there were some retransmits as the data dropped below. Basically, looking at the throughput from the network, certainly the network can carry the load. So we were quite pleased with that. We looked now, when we did get access to the DTNs, we did a throughput as a function of TCP buffer size. That's, you see the top right-hand plot. Ideally, that would be nice, flat, and go up and be horizontal as on a plateau. But you see, we did actually have some packet loss of order of 10 to the minus 2%, which was sufficient to suppress this. However, the throughput during the 60-second test flows was fairly smooth and increased after a plateau of about 5 seconds onwards. So again, we were fairly pleased that we understood what was going on, and this was using the what I would call the standard route from London, Paris, Geneva, Milan, and finally into Bologna. So this was the standard setup from the NRENs and GÉANT. We did try multiple TCP flows. So the way this was done is you set one flow going and you measure it for the 12 minutes. Then you set two flows going, three flows going, and then multiple flows. So in our case, for this particular test, the single flow was stable at about 22.5 gigabits. Three or more, the green line, gets 67.7, and four or more reach well over 82 gigabits a second fairly stably. So again, we were extremely pleased with that. We looked again at the test of moving data on two flows, and was that clean? The answer is yes. Here we ran for 12 hours. This would be similar to them moving their big data sets along, only we did it in a continuous run. So turning next to the work we did for the Bella launch, where we were using the Ella submarine cable between Fortaleza and Lisbon, Madrid, and Paris. And I had excellent collaboration with folks from RNP and Red Clara, and my thanks to them go for that as well. So that was the path we were using. We did compare it to the original path through the US, but I haven't got time to show you those slides, and they were only at 10 gigs. Going from Fortaleza to Paris, we had the absolutely classic throughput, TCP throughput as a function of buffer size, going up smoothly and plateauing at about the right place. We were using, by setting the affinity of iPerf3 to what I call the good cores. Those are the cores that are on the same socket as the 100 gigabit Ethernet NIC. This is important. If you don't do that, you certainly lose of the order of 5 gigs. Now, I have to say that we did find, similar to what Paul mentioned, in the opposite direction, wasn't quite as good. And the reason for that is that the CPU powers were different on the two machines. The RMP had more cores, but a slightly lower clock rate than the DTN in Paris. And this essentially gave a problem. We've seen this in other cases, which I will describe in a moment. One of the things that people find easy to understand is the time to move a terabyte. So we tried doing this, moving from Fortaleza to Paris. It's an 86 milliseconds. The routing was stable during all of the tests that I'm telling you about. And what we did was to measure the transfer every 5 seconds. Again, we used the set affinity to put the iPerf programs into specific CPU cores. And we used the TCP auto-tuning, having ensured that the kernel parameters, which determine how far you can auto-tune, was set well above the delay bandwidth product of this particular distance. So we found the single flow was stable at 30.5, and we'd run it for 13 minutes. And the transfer of 1 terabyte would take about 4 minutes, 40 seconds, which is pretty good. We looked at the performance of multiple flows, and you can see a very similar pattern that I described before. In this case, with 6 or more flows, we were reaching over 90 gigabits a second. But you can see that we were having retransmits because of the dips in the throughput. And then you would have an indication of the recovery times as well. Let me turn now to making measurements between Europe and Australia. And in this case, we are making some tests that go via the US and across the internet to a network, and then on to ARNet. And again, all this work with ARNet has been in collaboration with people that we work with on a regular basis in ARNet. Now, this, we got a nice smooth curve. It rises very, very nicely, but it only reaches just over 28 gigabits. The round trip time is 330 milliseconds. And if you did the delay bandwidth product calculation for 100 gig, you would need only about 3.7 gigabytes of TCP buffer. However, there's a problem. We have actually reached the limit of the TCP protocol, by which I mean, if we look at the TCP header, we have a sequence number, which the maximum is 2 to the 32, and we have a window. Maximum is 2 to the 16. Now, the window can be increased by negotiating the window scale factor in the SYN exchange, but again, that has a maximum, meaning the maximum window you can reach is 1024 megabytes. And the reason for this is that the window size has to be less than the sequence number to deal with sequence number wrapping and to be able to tell whether a particular segment is old or new. Now, you may say, well, this will never happen, it doesn't matter. Well, actually, unfortunately, at these sort of speeds, it could wrap every third of a second. So it really is quite an important thing to look after. Again, we tried doing multiple flows. In this case, it was 2. So the plot is showing the red circles is the first one we set off. And then a little time afterwards, we set the blue one going. And then the green triangles show you the sum of the 2. And again, we got a fairly impressive 56 gigabits a second to Australia. This was across internet too. And at that time, we were taking a quarter of their available bandwidth. So we didn't really want to do it for too long. One of the positives is that in these tests, no TCP segments were retransmitted. Let me move on to the path using the CAE1 link, and from Singapore to Australia, Perth, and then from Perth round to Sydney, the submarine cable, which ARNET is a member. So here we got a very similar behavior. In fact, we got up to about just under 30, whereas we got 26 via the US. In this case, there were a small number of TCP segments retransmitted, but again, we are on a production link. We felt this was a pretty nice demonstration of what's possible. The time to move 1 terabyte in this case turned out to be 4 minutes 32 seconds, again consistent. The test was actually running for over 16 minutes, and we moved 3.4 terabytes in total. This the CAE1 link gives us a much shorter round trip time of 259 milliseconds, which is pretty important when we're looking at these lengths and distances of transport. And then looking at multiple flows from London to Canberra. It is very clean and clear and what you would expect. The dips right at the beginning are part of the slow start. Of course, on this sort of length, it really does take quite a long time to open up all the buffers. And what you can see in the open circles is that 4 flows reach over 94 gigabits a second. And you can see there that there were some retransmits and the recovery time from there. Now, one of the things I should say in testing the other way around, the Canberra node is actually faster than the DTN in London. And what happened is that we ended up with let me be honest, a poor performance. But worse than that, packets were...
2 minutes, Richard.
Thank you. Packets were lost in the NIC of the receiving node. The network was not a problem. And basically, the ring buffers were full and couldn't be emptied in time because of the differences of transmit speeds, and only slightly. So this is a very good reason for what Paul mentioned at the beginning, that TCP pacing, perhaps done by the NIC, would help to solve this problem. And I think that's maybe we should be encouraging. So in summary, with tuned DTN nodes, we can demonstrate excellent TCP performance in all 3 cases. We've shown that a terabyte can be moved in under 5 minutes in all 3 cases with a single flow. Now, this may not be the case when we are got a real application and real compute environment. but we have demonstrated that a few number of TCP flows between suitably tuned ETN nodes can fill the 100 gig link. So my conclusion from this, and the keys to good performance, are detailed tuning of the DTNs. This is absolutely essential. Equally, one needs to ensure that there's a bottleneck-free end-to-end network path. This includes the NREN cores, which are probably very large anyway. The access links to the site. You don't want to be competing with other traffic, especially if your science traffic is estimating that it needs 80 to 100 gigs. It probably needs its own link. Within the campus, you may need a different way of connecting up, one that they're not really used to, like Science DM said. In many tier ones, that's already there, so it's not a problem. And of course, the DTN itself has to be properly connected. And I just threw in, because I found it really upsetting, that the packets get all the way across the network and then are dropped by the receiving net. So with that, thank you very much and ready for any questions.
Thank you, Richard. I apologize for interrupting you. I didn't know that the end is coming.
Oh, don't worry, Pavle. It was good actually to have the little prompt.
Yeah, I have just one small favor to ask you, and this is to upload this presentation to the Indico page or to send it to me so that I can do this. And
I will do that, no problem.
Thank you very much. So now I would like to ask the audience if there is any question for our presenters in this first session related to high-speed monitoring and high-speed data transfers. It is obvious that it is a non-trivial task to organize not just the network, but also the endpoints to transfer a large amount of data in short amount of time. So are there any comments or questions from the audience? Otto, I saw your hand, so please.
Yes, yeah. I was wondering what happened with the normal production traffic while you were doing your tests?
You're talking to me?
Or any of you, really?
Well, to be honest, when we were doing the tests using Internet 2, we didn't tell them.
Okay.
We did try and pick a time of day where we anticipated there wouldn't be many people using it, but of course, that science is,
it's hard.
Science is 24/7 around the globe, as you say. In general, we made no effort to stop production traffic. I think if I tried to do that, my network operations center would no longer speak to me. So we were running with it, but right. Trying to pick, like Paul, trying to pick times where we thought there wouldn't be much traffic, like the Australians were asleep.
Yeah, but ultimately the other traffic is TCP. You are TCP. In theory, your traffic will back off on congestion. We did notice with the Bella link that Raul and obviously Richard used as well, that you could look at the usage of that, the GÉANT, the new Brian or Brain, which is it, Brian system. You can see the utilization of that link. Maybe someone can post a link for it, but you would see typically that's running at 5 to 10 gigs, so it's not like it's heavily loaded, so you weren't really displacing much traffic. But the other thing you need to bear in mind is that in theory, any researcher at any time could run a transfer like this that actually is a real science transfer, and they would be hopefully getting good performance. So I know network engineers are naturally skittish at people loading up the network, but it's no more or less than a researcher might do if they try and transfer real traffic. So we do need to have networks that are resilient to that, but also use protocols that are friendly towards each other. I think Raul mentioned TCP BBR earlier. That in its first version was somewhat aggressive. So I think where we're promoting protocols and configurations for people to use, we should promote ones that are friendly to each other.
So question, was one able to check on the members of the lag In some cases, in many cases, when I was making tests, before I made the tests, I checked what the path I was going to use was using Brian. And I did notice that it was lightly loaded, so I would launch the tests and I would check that the individual members of the lag weren't congested. In many cases, we found that the way they've configured it, it's fairly intelligent, and if a lag is loaded, it moves on to another one of the members. Did that answer the question? In some cases, like going across the US, I had no visibility. Well, I did actually have some when I did it, but that's been removed because of security. And I had my ARNET colleagues checking their end.
Yeah, I would say that in the test that we ran from Surf, it was the same thing. First, we had an agreement between both sides that we were running the tests overnight. We used Brian all the time to check that we were not using the link at the time when it was very much used. Yeah. So we could see, for example, I was even running tests over this weekend, and I programmed my tests to run like 1 a.m. in the morning from 5 a.m. in the morning in UK. It means that in Brazil it was 10 in the night until 2 a.m. And we checked Brian, and also that because the tests were always tests of 1 minute, there was a certain assurance that we will not disturb things very much.
I've just posted a link to the Brian we keep mentioning in the chat there, so you can see it's completely open, so anyone can look at that. There's other bits of the network that you can get to if you browse around that system. It's the new GÉANT monitoring system, but it is SNMP based. It is polling every 5 minutes, so you have that sort of traditional limitation on what you see on the throughput. So, for example, when Raul was testing for 1 minute sessions, as he was explaining just now, you would see maybe 20 gigs shown as the throughput rather than 80 or 90, because it would average out over the 5 minute sample.
Thanks, Tim. I have one last question, and this is a general question, maybe for Richard, but maybe also for someone else from the audience. Is there a gap between the researchers who need this kind of huge data transfers and our community? We understand, I think now after all these tests, we understand what you need to set up and how to tweak and tune the endpoints in order to achieve higher data rates. But is there a gap between us and the researchers? I always have in mind those that are not always with some technical knowledge, something like molecular biologists, genome researchers and similar stuff.
Well, the answer is yes and no, I'm afraid. WLCG has regular meetings that include network folks from the NRENs, and they have the expertise to understand the network and tune it and run it for themselves. SKA, we have just set up an SKA NREN forum with a similar idea to allow requirements to flow one way and roadmaps to flow both ways, so that both sides have a feel for what the other might be capable of or might require. In other cases, it is, I think, not as clear, but I might be wrong.
I think there definitely is such a gap. I think Richard is spot on. The big experiments and those that have been running for some time have built the expertise and know how to work together, but the emerging disciplines that are trying to get good performance, it's more challenging for them. And the question then is, how do you close that gap? There is a GÉANT task force on research engagement development, I think, and they struggle to do this. From our point of view, it's useful maybe to be able to see what flows are happening over the network and try and see where the big transfers are happening, and that's where tools like NetSage, which we'll hear about this afternoon, are quite useful for understanding where the research flows are happening and whether they look as good as they should be, for example. But yeah, there's definitely a gap, but it's something that's very difficult to close, I think. It's a very good question.
We have a comment from Marcus. Marcus, would you like to share this comment with us?
Yes, I'm not sure if my audio is okay.
Yes, it is. Perfect.
I'm just commenting that from my experience, doing the troubleshooting or the network engineering part and finding the specific constraints for each given real path. So if you go from Europe to Australia, Europe to Brazil, Brazil to US, you have different constraints, different underlying technical limitations, and packing that transparently to the application or to the DTN, I think is the problem now. We probably need to have a fixed set of parameters that optimize most of these scenarios, and having that automatically set, or having global parameters that improve every scenario. And this is the problem right now. So we can work on that on a pair-by-pair basis, which is not scalable.
Thank you, Marcus. Okay, with that comment, I think we can end this first session. We are just 4 minutes late, so I suggest not to have 6 minutes, but instead 11 minutes of break, of coffee break. So we will return at 15:25 Central European time. So yeah, take a bit of rest and see you then. Okay, welcome to the second session of our workshop. Our first presenter is Ljubomir Hrboka from CARNET. Ljubo will tell us something about data analysis on the PMP nodes that he's been doing for the last couple of months within our task for package 6 task 3. Thank you, Ljubo. We see the presentation. And we can hear you.
Okay, thank you. So here is a couple of slides from the PMP data analytics that actually I've been doing for the last almost a year or so. So this is the story about the data from the GÉANT performance management platform, PMP. Actually, we have a number of small nodes scattered across Europe, some of them also in Asia, a couple of them also in Africa. And there are 5 GÉANT nodes, and small nodes are configured with the measurements towards GÉANT nodes, and all the data are saved on the central storage. And data sets that we have available are standard personal measurements like latency, jitter, RTT, throughput, HTTP, DNS. And we have a couple of years of measurements available. And data are standardly accessible in JSON format using the REST API. So the idea that we have a central data storage with all the performance data from various networks links brought up the idea of using machine learning algorithms to try to detect an anomalous on link like slight degradation that are not that do not trigger alarms, or some other deteriorating conditions that can happen without alarm being triggered, and basically to have a holistic view of the network performance. So we decided that our final goal is to develop a machine learning model that would be able to detect network anomalies, basically to help pinpoint ongoing issues in the network, or to facilitate network planning, etc. So these are the steps that are normally included in some machine learning model development. So data collection and data pre-processing, these that are colored in green, are actually something that is done by now. And right now I'm focusing on these parts that are in yellow, like choosing a model and training and evaluating a model. Of course, still some of the parts of the data pre-processing is not finished. And at the end is this red part that is actual model deployment, and we hope it will successfully happen in the next. So, okay, I will not specify the time, but maybe a couple of months or maybe a year. So right now we are here performing data analysis on the real performance measurement data. And in this presentation, I also prepare, but I'm using in my work a lot of data visualization to easier understand the data and interpret the results. So why is so important to understand the data? In machine learning, there is a principle that states garbage in, garbage out. So basically, if you don't know what you put in, you probably get some wrong results. And exploratory data analysis is something that should be done on all data. So observing, categorizing the data, looking for the missing values, outliers, correlation, visualization, etc. And all that work is being done in the last year or so. So what we actually have, first, what real data do we actually have? Let's say the largest amount of data are from the POW stream latency and jitter measurements. And nominally, we have one histogram of 600 packets every minute. And this is actually the finest resolution that we have. So our measurements do not include packets one by one, but only histograms. Our archive includes only histograms, so we don't know what happens within that minute. And that's the finest resolution that we have. Jitter is also there in 1 minute resolution. Throughput is only 4 times a day. That's a nominal value. From the real data, this does not happen like that. Sometimes we have 2 measurements, sometimes we have 3, sometimes 5. That's depending on the schedule and load on the nodes, etc. And then we have measurements like RTT and traceroute that are happening every 10 minutes, and HTTP and DNS measurements every hour. So what I've been mostly doing is creating procedure to perform the analysis, like we have a JSON files, and then I had to create some kind of data pipeline, and mostly using Python architecture, and heavily relied on the NumPy library. And from the machine learning point of view, there is no label data available, so I had to and I'm right now doing tests with models that include unsupervised learning. At the end, in parallel, we've been developing the page scheduler graphical user interface for on-demand measurements. And since there is a part of it which consists of a proxy server that is built in Python, that is actually the pretty good place to put our testing and deployment at the end. So we are in parallel thinking about these possibilities. And now I will just show you some of the results from the various measurements and analysis. So just to to get a feeling what's going on here. So basically, this is something that is result from this graphical on-demand user interface. This is just the example of, let's say, normal histogram versus anomalous histogram from the 1,000 packets result. On the upper graph, here we have these one-by-one packet measurements. Because they are not performed to through the PMP platform, but this measurement is performed from the personal graphical user interface. And the bottom graphs show the histograms, and these are actually available from the PMP measurements. So you can clearly see the anomaly that's going on in this 1,000 packet measurement. And now what we mainly have is the latency and jitter measurements. So I started with those one because there is a huge amount of data available. Like here is a couple of months, there is about 30 million samples. So this is from one link measurement, and you can see the normal link upper picture would be something that is normally seen on the link, and you would tell that this link has about 19 milliseconds delay. But if you amplify these anomalies, you can see on the bottom that you can see these spikes, and lots of stuff is going on there. This is only shown the samples below 50 milliseconds. And actually, we have the tool now with the Python and all the NumPy libraries to get some kind of lens and see what's going on with anomalies. So here we have some example, which can be a measurement error, but it also can be some real anomaly. Where we have delays about 4 seconds. So this is the maximum delay. I think it's on the previous slide. It's 3,799 millisecond delay. And this is exactly the time when it happened on this link. This is that finest resolution that we can see. We cannot see these packets within minutes. So we have only the distribution within 1 minute. And then we performed these measurements on the different links, and we have some other findings, like this number 4 here. We can clearly see in the bottom part, in the left part of the x-axis, that we have the dots with the delay of about, I don't know, 1, 2, 3 milliseconds, and that is clearly the measurement error. Probably from the time drift or something, but there are lots of measurements error here. Okay, enough data is available that can be said that it's normal data, but we have to, when we are training the model, it would be better to eliminate those that are clearly in the area of errors. And this is one of the interesting pictures. This is the one-way delay distribution of packets on the same, between two same endpoints, but in different directions. So you can clearly see that there are different distribution in different directions, but the link is pretty much behaving the same. Then I have experimented with various correlations between different data. You can see here one throughput measurements in the, I don't know if it's visible here, it's hard to read, but this is 2 months, I think, period, 2 or 3 months. And on these points where the throughput measurements give low values, so something happened, either it was an error or in measurement, or it was a real anomaly. And you can see here correlation with delay and jitter. And in this example, there is no correlation. So this was probably some kind of measurement error. But if you take a look at the next point, this is the same throughput diagram, but in the next point, if you can see the jitter at the bottom diagram, and you can clearly see that this is at the bottom, this is a minus 10 minutes from this point. And you can clearly see that there was also a jitter outlier in this point. So this is basically the stuff that I've been dealing with, and trying to a lot of things are going on now, but I don't have results from the model development, so I cannot show you that. But I'm right now starting to prepare the machine learning model, and I'm still trying to develop a model that will be okay to detect the anomalies and evaluate it. And at the end result, this is the opportunity to create some kind of system that will be able to correlate multiple results from multiple measurements, and in the end bring some, let's say, new features in error and anomaly detections. So this is all from me. If you have any questions, please ask. Thank you.
Thank you, Ljubo. Also, I will ask you to either send me your presentation or to upload it to the Indico site. I'd say that we still haven't solved in this work what to do with the data lake we are creating with a lot of measurements that we have, but this is something for our further discussion. I will leave this discussion later for the Q&A session. Our next presenter is Fabio Farina from GARR, from Italy. Fabio will present us his results on analyzing the data from the Timemap system. So I will not speak instead of Fabio.
Yes, can you please confirm you can see my screen?
Yes, we can see the screen and we can hear you loud and clear.
Perfect, thanks. So good afternoon. I wish to thank the previous speaker because it explained the problem statement, so I can save some minutes, because I'm describing essentially the same goal we are trying to reach, but in a slightly different way, using different tools and approaches. So first of all, today I'm going to introduce the Timemap service, its purpose, its current status, and then I'll dig deeper on the anomaly detection approach we follow. So essentially, the need for Timemap is given by the fact that most of the weather map tools available do not allow a clear observation for time-sensible metrics like latency and jitter. Most of them just focus on capacity, on bandwidth. So when you need to tune some modern applications, what you need to know is not only if your network segments are congested or not, but also if the traffic is flowing in a nice, regular, stable, and predictable way. So because of this, we realized that we needed something different, and Timemap is a weather map tool that allows to collect and represent jitter and latency information from the GÉANT backbone. And Timemap exposes this information using an interactive graphical tool. Essentially is based on Grafana and all the related tool sets. In particular, the push for having Timemap is the growth of high bandwidth, extra low latency need applications like LoLa that are getting more and more important during these years, mainly also because of the pandemics. So having a tool that allows to keep control and keep track of the historical evolution of the status of latency and jitter for the links of the GÉANT backbone simplifies the debugging and troubleshooting tasks for the users that are trying to set up links for LoLa sessions. Because essentially, if we are able to keep track of the status and the health of what's going on latency and jitter on the backbone, then we can be safe, be sure about a huge segment of our setup, and we can focus on debugging just on the endpoints, on the last mile connectivity essentially. So, for example, during a LoLa session, it's not just a matter of having high bandwidth connectivity, stable connectivity, but also the round trip times must be bound, must be constrained and stable. And we need to be sure that the jitter also is very stable and very constrained, because in terms of human perception, jitters has a higher disrupting level on the perception, for example, of a musical performance. So given this context, given these requirements, we developed the Timemap. And Timemap essentially is an ETL classical architecture. So we have a data normalization layer that collects samples from the GÉANT backbone devices, plus some additional endpoints that are personal machines. It focuses on using Juniper real-time performance monitoring for getting data from the devices, and it uses T1 or TWPing for sampling from personas boxes. In the last weeks, we are also working to use T1 directly from the Juniper boxes. So we are trying to uniform the acquisition protocol. The central component for the architecture is essentially a time series database built on Docker. And on top of that, we have the graphical user interface features, the analytics that I'm going to discuss later, plus all the security related features. Timemap supports AD-gain authentication and has a pretty rich role-based authentication approach, so that we can control data exposition to end users according to their roles. As an implementation strategy, we decided to use as much as possible open source standard tools. We are not working in FUPI6 T1 on developing a new tool in this context. We are trying to study the behavior of the network itself. So our focus is not developing new code, but is to just use as much as existing code, standard stacks are there, just developing the essential Python scripts that are needed to collect the data. Then we rely on Telegraph, on Influx, on Grafana, and plus some custom HTML and JavaScript scripts just to prepare the look and feel and control the overall process. We run on Docker because it's lightweight, it's simpler to manage the software lifecycle. And also it's easier to hand over our solution to other partners. For example, we are handing over the current Timemap implementation to the GÉANT NOC operations. So they are adopting the system, and GARR as well is, of course, looking for adopting this approach. If you want to have a try on the system, this is the link. The code is open source and it's available on the GÉANT GitLab. So just running quickly on the look and feel of the Timemap GUI, the user sees the topology, and by interacting with the items can extract the RTT and the jitter information for specific links and specific devices. By using Timemap, and we are collecting data since I think April of last year, we got useful insight of the behavior of the network, and we have been able to see interesting things like regular or anomalous trends, and spikes or misbehavior given because of commercial circuits that were misbehaving, or strange behaviors given by periodic rescheduling, periodic routing changes. So given that now we have a relevant number of observation, the next step, of course, was let's try to see if we can see automatically something interesting from the data. Most of all, we were interested in getting anomalies. And the goal for anomaly detection is having something that can generate automatically alert. And at the same time, we want to use anomalies to cross-correlate events happening on devices or on links. We had further constraints on the anomaly detection machine learning strategy that we wanted to follow. And we wanted something that is lightweight, can live easily without too many dependencies in our Docker deployment framework. And most of all, we wanted to have robust estimations in terms of algorithms and real-time processing. Given these constraints, and given that, as it has been explained in previous presentation, anomaly detection is essentially an unsupervised task, and it's just a way to classify standard deviation for time series in the end. We decided to adopt two quite standard families of machine learning algorithms that are random trees and support vector machines. And in particular, we decided to adopt a Python library that is called River, that implements pretty rich family of streaming algorithms. The peculiarity of streaming machine learning algorithms is that they can work with single points rather than the traditional training sets and validation sets. So each point is learned by the classifiers and is classified by the algorithms. For Timemap in particular, we adopted both the families, because we wanted to apply a pretty standard trick in machine learning that is called model bagging. So essentially, we tuned the models so that each model has a 3 sigma accuracy in prediction, and then we combine the prediction for both the model, and we mark a point as anomalous only if both the random forest and the support vector machine state that the jitter or the latency point is indeed anomalous. From the architectural point of view, as I said, the River sidecar container is just one more Docker container that reads data from the influx database, processes the points and marks with a flag the points that are anomalous. One another point that relates to the way we apply machine learning models to the network topology is that we decided to train our models for each link of the backbone network, as the streaming approach and the specific machine learning algorithms we chose are lightweight. We can keep track of a model for each network segment without jeopardizing too much the memory and the processor of the virtual machine that is running Timemap. Mainly this is because we are adopting streaming algorithm. So we just needed to keep track of the model status and not huge collections of data points.
Fabio,
Well, in the end,
2 minutes approximately.
Yes, I'm closing. What we get in the end after all this talk is that that pale yellow point on the data point itself, and that is a marker that the observation is considered as an anomaly. On a wider time frame, of course there are more anomalies depending on the observed link. What about the computing efficiency of our approach? We have a really coarse sampling frequency right now because Juniper devices perform RPM and T1 tests once every 5 minutes. But the algorithm is quite efficient, and the implementation is lightweight as we expected. So we are able to observe and train 3,500 observation every microbatch, and every micro batch, sorry, is completed in less than 3 seconds. In general, we are pretty satisfied about the way the algorithms learn the anomalies, and debugging is really effective because after some cycles, we can see that the number of catched anomalies decrease and then becomes stable. I wish to say that when the container starts, the models are warmed up with a pre-training period with no forecasting of 2 days of data. So we have that warm up drop at the beginning of the training. And what I have to say to conclude, the anomaly detection tool is up and running since 10 days, has been running for 10 days, sorry. The behavior is what we expected. The streaming machine learning algorithms work really well, and everything is less than 200 lines of Python. And that's what we wanted in terms of footprint and complexity. What's going on about Timemap in general? As I said, we will go on with the handover to GÉANT operation for the tool. We will go on with the involvement of more RNs interested in time maps or in this anomaly detection approach. And as anticipated, our next steps in terms of development is asynchronous events notification and anomalies correlation. And that's all, and thank you.
Thank you, Fabio, for your presentation. I put one comment in the chat, and we can leave this for the Q&A session. and discuss this later. I would like to invite now Nichloas Buraglio from ESnet. I guess I saw Nichloas is among the participants to his presentation, because I believe that this one will be presented by him.
Let me get my screen shared here.
Yeah. No, I saw also the APAN agenda and saw that you have your presentations over there at the APAN. So this is a bit unfortunate fact that this workshop is happening on the almost the same day as your activities over there.
Yeah, no, it's not that big a deal. Can you guys see the slides?
Yes, and we can hear you.
Okay.
So,
yeah. So yeah, the APAN originally Kieran was set to give these, but she's had she's unable to at this point. So the other partners in this project, myself and Scott Campbell, we're just splitting the two. So I'm here and he's going to do the APAN talk. So no big deal at all. So with that, I will go ahead and get started. Like many others, we're looking at the machine learning based approach for optimization of networking and specifically in path optimization. And I want to thank the prior two talks really set a lot of the framework up for that. So makes this significantly easier for me. So a little bit of background, as we've all seen, within the last probably 5 to 10 years, we've had a lot more move towards automation of networking. And even with that, there's still, a handful of challenges since, for one, networking has become essentially a utility. So very important for work and school and all of those things, much like, the electricity and stuff, we just kind of expect it to be there. So what we did is, we tried to take a data-driven solution to help learn patterns, across multiple links and then, improve on existing protocol stack response times and capabilities. The three problems we really wanted to solve were, how do we deal with unpredictable usage patterns, which we saw a significant amount of, towards the beginning of the COVID lockdowns here. Utilization across not just ESnet, but many internet providers was very unpredictable because no one had kind of expected those things to happen. How do we deal with large, complex network topologies that are changing and growing all the time? Another, pretty significant problem. And what do we do with devices that may have restricted capabilities? So what we really mean by that is, how do we deal with a brownfield network, something that already exists, that can't be replaced, that has a fixed set of capabilities, and how do we leverage those? Because as anyone that's run a large operational network knows, you can't just take everything out and put in new stuff for many, many reasons. So we wanted to be able to work with what we had. Now, in today's networking, we have, deterministic routing algorithms, which are mostly manual, manually set up by engineers, changed by engineers. At the very best, you probably got some automation that might happen and maybe some SDN pieces in there. But for the most part, it's shortest route and least hops for moving data around in really big networks at one, stage or another. That can lead to congestion and packet loss. And as we all know, TCP is very sensitive to that. And so by definition, it's sort of inefficient utilization, right? Because it's essentially, I know that this path is the one I want to take because the routing protocol tells me that, unless I go and tune it, in which case it's going to be this other one unless it fails, and then it'll take the backup paths. That works, obviously, we all do it that way. But as far as utilization goes, it's not necessarily the best option. And the other thing that we wanted to address is, for the most part, everything is reactive as far as fault tolerance goes. So I see a failure and then I have to action on that failure. So we took some of the concepts of, self-driving and we applied it to networking. and created this adaptive traffic advisor, which takes in not real time, but sort of nearish real time data for path decisions and analysis. And more importantly, it provides context, because the context is what gives you that rich set of things that you can do extra stuff with. So it learns to avoid the congestion if it can, and therefore packet loss. It lowers the, by lowering that congestion, we get better TCP performance. We can better utilize the links we already have because we can do spread across them. And, in a perfect world, when we have all of the data and all the learning's been done, we can do proactive fault repairing. We can sense some of the things that are happening based on the data that has been learned from. This is kind of a high level diagram of really what happens, right? At the bottom, you have an environment, state gets fed into the agent, action happens based on that. If the action is correct, it gets a reward. Typical machine learning process here. I don't want to go too deep into this, but it's essentially deep reinforcement learning is the basis of what we're doing here. As I alluded to earlier, we saw some performance changes at the beginning of the pandemic. We actually wrote a paper on it that was published, and a few of the things that came out of this: how do we deal with surging of traffic on networks that are heterogeneous, and how does that affect performance? So as we started down the path of working on this, we realized that every network is going to be different, all the traffic's going to be different, so it's in theory going to need all this human interaction here. So we wanted to address those things with what we were doing. So we built this thing called Hecate, and essentially we call it that because we say it performs black magic on the network. So what it really does is it monitors the health and activity, and it can reroute traffic based on what we're currently using, which is LSPs. So we built most of this currently around segment routing, because that's what ESnet 6 is. So ESnet 6 being the current state of our ESnet's backbone. It doesn't have to be segment routing. That's just how we've done it. We purposely built it to be modular so that it can be planted into really any network that can generate flow data and some sort of performance metrics from what we're using as perf sonar. But what it does is it creates these traffic classes. So we define these traffic classes, and then we learn from the data that's ingested, and then we give the operator an initial choice. Do you want to do your traffic classes based on latency, throughput, jitter, a number of different options? The operator can make a choice, and it will re-optimize the network based on that. And it does that by employing passive and active learning. So it learns from the historical data, and then it actively learns by probing through the network periodically and by leveraging monitors, in our case, perf sonar systems. We could also ingest 2-amp data from network devices or any other type of performance data that's available. It's a reasonably fast reaction time. It's definitely not real time, but it's on the order of however long it takes to roll over a flow data record, ingest it, and crunch the data on it. So it's minutes. And it's deployable, most importantly, as a hardware solution. So you can take it, it's not just a piece of software, you can actually push it down into an FPGA and have faster reaction time because the hardware is processing the data. A little bit deeper look at kind of what we're doing here, the deep reinforcement learning piece, the actioning, the completion time, and that. The observation really, I think, in the deep learning part is the meat and potatoes of how we're doing these things. The constant feedback loop here that we've got allows us to be constantly learning about the current state of the network and the very brief historical state of the network. So then we can predict what's going to be coming next. So as we went through this process, we had a handful of observations that really helped inform what we were doing here. The data analysis that we did using the unsupervised stuff. The unsupervised learning was a little bit slower, but it allowed us to do things like a faster update cycle on the link attributes. And we got that data not just from PerfSonar, but we can also see data from, many other aspects of the network, such as syslog data that reports on optical levels and things like that. We created the 3 active classes. These are currently they're manually created, Jumbo, Interactive, and Default. And as I said earlier, we're feeding it the data from NetFlow and PerfSonar currently, as well as some other sources. What we do with that data, I think, is probably a little more interesting to this group. So we create these 9 buckets of data. And as you can see on the right here, we classify them with the darkest being the most common. So in our network and the tests that we've worked on, the most common for us is medium time, medium volume. So sort of right in the middle of the road. This changes over time, depending on what's going on, but over the course of the data set I'm talking about here, the most data that we had flowing through the network was of this sort of right in the middle, not mice flow, not jumbo flow, just sort of middle of the road, rounded out. We also took into account the fact that 9 data points is quite a few. So one of the things that we did as we were creating this data store, for lack of a better description, is that we process all of this data into a custom format metadata that then is stored in a database. And as we do that, we take these multiple data sets and we combine them. Okay, so we'll take 2 data sets and we'll combine them. So like we can get velocity as a 3-dimensional data set by taking 2 2-dimensional data sets. It allows us to more efficiently deal with the data, because 9 pieces, 9 buckets is too many. It's all unlabeled data, so clustering is unsupervised. We also think about links a little bit differently. In keeping with the way that PerfSonar works, we think about each link not just as a single thing. Each link is actually considered 2 pieces. From the networking perspective, at the optical layer, you look at, I have a TX and an RX, and combine those together, I have 1 link. You can't have a link without both of those. So we break those apart and we look at those links as 2 different data sets, TX, RX. Because as you can see, the performance on a link can be dramatically affected by the path in one direction. This graph on the right shows, significantly worse loss in one direction than the other. And so we think about those as 2 discrete entities across our entire network. So it's really 2 networks that we're looking at. One is from the perspective of which device we're looking at, the TX, and one is the RX. And so we consider that as 2 sort of complementary entities, but separate because of the way that that can affect performance. We also have what's called our orchestrator. That's the piece, this robot right here, that performs the actions. And as I stated before, this is built around segment routing. And so in segment routing, you can have, which is a standard protocol for anyone that's not familiar with it. It's sort of the next evolution of MPLS. And you don't have to, but you can employ a controller with segment routing, and that controller has a knowledge of the entire topology of your network. It also understands all the label switch paths that have been created. So if I want to create a circuit from site A to site B, and I want to put this traffic over it, but I want it to take this specific path, the controller can instantiate, and it knows all the data about that. So our agent talks to that piece of software and is able to say, well, this link over here maybe not optimal at this time, so I'm going to move it over here. I'm going to see congestion here. So I'm going to move the traffic flow over here temporarily and move it back. But it does that based on common APIs, and it does that based on not just the data, but also how the optimization has been set up for the network. So if we tell Hecate to optimize based on throughput, it's not going to weight things like distance. So if I have a better path from A to B that has 4 hops, I can tell it to push it that way, whereas standard routing would tell it to push it, with fewer hops.
There is 1.5 minutes, preferably. So please.
What's that?
1.5 minutes you have.
Okay, I'm almost finished. This is I kind of went over this already. This is really kind of the mechanics of how it works. We feed the information from that middle layer up into Hecate, and Hecate has these different buckets and containers that it has the capability of optimizing on and leveraging. And then in turn, it feeds back its actions into the existing solution. So PCE, segment routing, an SDN platform, or traditional traffic engineering, such as MPLS-TE. And that in turn pushes it down into the hardware. And then you have the cycle of the monitoring, feedback loop. So this is sort of just the mechanics of how it works. Right now, the prototype is currently being tested and deployable on Raspberry Pis. We're working on the second prototype that's using some FPGAs for classification at the edge and to make higher computationally expensive decisions. And just a quick example here, if we were going to run this on a topology, something like this, 5 routers with multiple redundant paths, we could, in theory, class the traffic into 3 categories: jumbo, interactive, default. So you've got your high performance stuff, video, conferencing, and then just everything else. We take into account loss, delay, and jitter. And then if we were to choose an optimization path, let's say throughput, before we ran Hecate, link 4 would have more traffic on it. We look back here, that topology. After we run Hecate, it's a lot more uniform and better optimized so that you're able to get more utilization out of links that maybe in traditional routing wouldn't have traffic flow over them. So quick conclusions, deep learning is extremely effective method to allow for systems to learn to self-manage. There's a lot of challenges involved, and there's model-based learning such as NetPredict that already exists. This is sort of related to that project. Miriam is involved in both, so we're able to take what we need from that. Retraining is also a consideration if your network needs is highly dynamic, so you have to the training always has to continue. And right now we're working on GPU and FPGA installations for faster reaction time. And that's it. If there's any questions.
Thank you, Nick. Yes, now is the time for this Q&A session. So I would like to ask anybody from the audience whether type the question in the chat or to ask the question.
Your audio is breaking up a bit, Pavle, sometimes.
I apologize. I hear everything well. So if there are any questions, please raise your hand, unmute the microphone, or type it in the chat. Yes, Otto.
Right, I have a few questions. Perhaps one first for, should we do the latest first, perhaps? For Nichloas then. Oscillations, when you do routing based on throughput or traffic load, you didn't mention that, but I assume you handle that somehow. I mean, when you reroute your traffic, you influence the traffic load of the whole network, and this might again influence your routing algorithm, which can cause it to reroute back again, when you can get this effect.
So we've actually worked around that by using LSPs. So segment routing relies on the substrate IGP. So it's relying on in our case, IS for the the internal routing. The segment routing lives on top of that. So we're using LSPs to move things around. So the underlying routing always stays the same. We're moving around circuits that are containing that, the data that we've specified.
All right. Okay. So the other traffic just stays as it is.
Yes.
All right. But when you move your own traffic, I guess the whole network looks different afterwards.
Yes.
Okay. But it's handled. All right.
And what about SDN switches? I mean, are you not trying to optimize the traffic, especially the segment by segment through SDN?
So do you mean like using like OpenFlow or something?
Yes.
So the OpenFlow work happened at the very beginning. Most of our concentration has been on segment routing because that's what our network runs. But if you're running it within OpenFlow, it really just needs to talk to the controller to move the, to create the correct rules. I'm not sure exactly what you're asking.
Yes. So actually, I was asking if you have tried that also, but as you said that you're actually based on the routing and something that's already deployed there. Apparently, that's the focus of your work then. And
yeah,
that's if there is a comparison between this approach and the other approach, and if you can gain some insight from you about that.
Yeah, I mean, they both definitely have their advantages, right? I mean, the way we're doing it now is for scale, right? Because segment routing scales to just gargantuan proportions, whereas OpenFlow typically, your distance from the controller is a consideration. So if you're, and it's totally, using Faucet, this is totally doable. The question is really, how big are you going to scale that, and how far is the controller going to be from, wherever the devices are? So if you have, let's say, geographic areas that each have their own controller, there's nothing saying that Hecate couldn't talk to all three of those and and optimize based on those specific areas. But that was the initial work was actually done with Faucet and some SDN switches that I have here.
So Nick, what do you see as a main obstacle for implementing such thing in production network? And what do you think should be resolved before doing such a step?
I mean, I think the main obstacle is that anytime you have autonomous processes that are affecting the network that are new, there's an amount of skepticism that may be involved with that. Rigorous testing needs to happen to make sure that this sort of new thing isn't going to cause unnecessary and unforeseen interruptions in service. So I think that really the biggest impediment is really just having all of the testing very comprehensive and done beforehand in an environment that very closely resembles production. And that's actually some of the stuff that we're working on now. We've got a very comprehensive orchestration platform that we built at ESnet. I'm actually going to talk about it at TNC coming up, but the goal is to get this worked into that workflow so that it just is part of the process. And realistically speaking, I think we've got a little while before that happens. We still have quite a bit of polishing that needs to occur, and documentation that has to be written and all of those things to make things production worthy, and none of that's really happened yet. So I think those are probably the largest impediments.
Thank you. Otto, you've raised your hand again, please.
Yeah, I also have a question for Fabio. Perhaps you mentioned it, I can't remember, but these anomality detection systems you have for your Timemap system. have you any plans of using them for forecasting in the future? Because I mean, when planning time-sensitive online events, it's really what's coming up in the future, which is important.
Well, I think no, honestly, because getting anomalies on what you see, it's a simple task in the end. But doing prediction requires that you understand the dynamical system that's behind the behavior of the metrics, and it's a really complex task. From a mathematical perspective, that's feasible, but I'm not sure about the result. This is something that's in my to-do list, but it's very low in priority. Most of all, it does not fit with the Timemap constraints because it's a task that needs a lot of data and a lot of batch processing to extract the models, because as a methodology needs deep learning tools like deep autoencoders and things that are hardly run and trained in real time. And with Timemap, we wanted something that we're not consuming more than 100 or 200 megabytes of RAM at all.
Just one small question.
Yes, Pavle, I would like to answer the question you wrote on the chat. The answer is that no, I have no idea what's going on with that anomalous point, and in general, so far I have no idea what's going on with any of the points that are marked as anomalous, because anomaly detection algorithms just state that a point is an outlier with respect to the statistical distribution of the point you're looking at. That's why I said that anomaly detection is just one step toward the cross-correlation of anomaly events. Once we are able to get simultaneous anomalies coming from routers that are in some way either connected by physical links or on the same path in cases of persona measurement, then we could have some more useful hints about what's going on the network.
Thank you, Fabio.
You're
okay,
welcome.
I will have to be again the timekeeper. I mean, we are, given the fact that the agenda is quite packed, I think being late, just 10 minutes is fine. But I suggest that we go for the last segment of our presentations, and we will have another Q&A session after that. So if there are any remaining questions, please type them in the chat and wait for the last session. So now I would like to invite Shawn McKee to share his screen and presentation and to start presenting the SAND project.
Okay, thank you.
Thank you.
So, thanks to the organizers for inviting me to talk about the SAND project. I'm speaking on behalf of the SAND and OSG collaborations. And a quick overview of what I want to try to cover quickly. First, a little bit about WLCG OSG networking and what the original motivation for SAND was. Some details about the project, the goals, and the outcomes. SAND is actually a concluded project, and I want to go over what we actually achieved. And then at the end, discuss where we're going from there and how we're continuing the SAND work. So OSG has been supporting networking for over 9 years. We're really trying to help our users and affiliates in identifying and fixing network bottlenecks. To do this, we've created a very comprehensive network monitoring platform. And our goal is to improve our ability to manage and use network topology and network measurements for analytics. There's associated work that's done through the WLCG Network Throughput Working Group. This group was established to ensure that users and experiments can better understand and fix networking issues. We actually use that group to oversee and manage and maintain the perf sonar infrastructure that we have globally deployed for the WLCG sites and the OSG sites. We also work to coordinate network performance incidents, so we can be contacted and help identify whether or not a problem is really related to a network issue or more related to the end sites. And often we can resolve issues within the working group without even having to go further based on the information we have available. So the SAN project was generated in that initial work environment. It's an NSF funded project. Our idea was to combine, visualize, and analyze all the different types of network data that we were gathering. You know, the sort of meta goal is capitalize on this rich data set, make it useful. The project started in 2018 and finished last August, and you can see the PIs, Brian Balkelman and Rob Gardner and I were co-PIs. The context that we started in, there were a number of projects that were doing work in networking that were very closely related. We had the core work within IRIS, HEP, and OSG, operations support, coordination, and development. And then we had these other bubbles out there doing different work. The SAN project was focused primarily on the analytics, the visualization, the alerting, and alarming. But of course, we worked closely with the perf sonar team, WLCG throughput working group. And at the time, there was a HEPIX network function virtualization working group, which has since concluded its work as well. So SAN was trying to create these new visualizations, analytics, analysis of all the data that we have. The initial architecture had a data pipeline that went to an ELK stack. We had visualizations in Kibana. We had a number of tools. We had sort of a plug-in architecture. And the focus was to create alarming dashboards so we could see interesting events, anomalies effectively. And very importantly, try to correlate measurements with routes. And the network routes that we measure are very dynamic and an extensive amount of data and could be a very powerful tool for helping us to localize what's happening and where. And then finally, an alerting system based on the data. One of the things that we got early on when we deployed perf sonar were requests to from end sites who deployed it. They wanted a place to go where they could get information if their site was involved in a problem. Is my site having a network issue? Is my site the source or the sink of data that's having a problem? They wanted to know that. And so that was one of the goals of the SAN project. So we developed, hardened, improved the network pipeline that was in place. Schematically, this is shown below. We have the global deployment of perf sonars, and we have a number of components that help us monitor, configure, manage, and collect data. And the data actually goes to a number of locations. We have two different Elasticsearch instances. We back up data on tape at Fermilab. We send data to the Monet architecture at CERN. And then all of these locations then have the ability to provide user interfaces and provide interesting ways to look at the data. SAN, as I mentioned, did conclude, and there were three main areas that SAN provided some outcomes. We were very successful in hardening and evolving the network metric pipeline that we had developed. We moved the pipeline into a central Rabbit MQ bus. And as you saw earlier, that allows us to push data onto the bus and then have a number of different ingesters that can grab the data and send it to different locations, transform the data, augment the data. We also changed so that rather than having to pull the data from the global set of perf sonars, we could actually have them publish data directly to the bus. And as mentioned, we also pushed data onto tape at Fermilab. We also developed, prototyped, and then put into production an alerting and alarming system, and I'll have a slide on that in a second. As noted, it was one of the most requested features that we had gotten for sites that deployed perf sonar. We're still continuing to evolve this and tune it to make it more useful. And lastly, we've been doing a lot of work, as we've heard today, in a hot topic, machine learning on this data. It's very challenging. Anybody who's tried to work with all the wealth of network data has probably found that there is a lot of noise in the data. The individual tools themselves have some challenges in producing reliable measurements or consistent data. And you have the challenge of a dynamic infrastructure where paths are changing and multiple metrics that are being measured across that infrastructure. So we've been, as initially done in the SAND project, was trying to create annotated data sets. So as we heard before, there are anomalies that you can identify statistically. What you'd really like to do, though, is identify real problems and their signature in the data. And so you'd like to be able to teach a machine learning algorithm, here is failing optics, here is a bad patch cable, here is, you know, a problematic end site application. Things that you might be able to glean from the set of data. And so our goal with SAND was really to try and lay the basis for that. And I'll describe at the end where we're going from what SAND provided. I've mentioned a number of things. I think one of our biggest challenges has been the network topology, because whenever you make measurements across the network, you know, the first important question is, what path were you actually measuring when you got that result? And so by identifying the paths accurately and tracking them, that gives you a powerful basis to work forward using the metrics that you gather over those paths. And there's a lot of power in this as well, because there's the time component, there's the physical path component, and there's the measurements you make. And so, for example, if you think about 5 host pairs that suddenly show a significant increase in packet loss at the same time, you know, what's the inference you can make by correlating those paths? If you take those 5 paths between the 5 source destination pairs and correlate them, if they all overlap in, say, one link, then you've identified both the time and the location of the problem. And so that was one of our goals with SAND, was to try and do those kind of correlations. We do make a lot of traceroute tests between our persona instances, but as noted, the data is very large, very noisy. We did some initial work with the McKee group, and they created a nice tool that lets us dynamically look at the route information. There's a video of the first release, and I'll show later a link where you can actually get to the McKee tool. It's sitting in front of our Elasticsearch data. In any case, the WLCG and OSG continue to work on identifying anomalous path data for alerting and alarming, and as well as to get that data ready for machine learning that we would like to be able to do, identify root cause and types of issues. So alerting and alarming, much of the SAND project was working to develop a system that would allow users to be alerted when problems happen. So on the right are a couple screenshots of what the alerting and alarming interface looked like. We use federated identity to log in. Users can log in and then select and filter alerts that they're interested in. This actually continues to be developed and expanded as we come up with new analytics, new ways to identify issues in the network. We can add them here and make them self-subscribable for those that are interested. Another thing that we did a lot of groundwork in the SAND project was in developing analytics. So how do we take all the data, clean it up, organize it, and then actually do something useful with it? So we had developed as part of the project, a dashboard based on Plotly. We have the link here. And this was sort of our test bed. We would get new algorithms, new functions, new ways of filtering, organizing, sorting, and ranking data, and we would test it out in this dashboard. And then this actually serves as sort of our prototyping space. When we get useful things, we actually then migrate them back to the alerting and alarming dashboard that I just showed. So this is kind of our quick and dirty prototyping platform for new analytics. We've got a lot of information. I've only shown a few things, but there's a number of resources that we have or that we know of that are related to networking. And when end users want to find or locate this, we kind of needed one place that they could go to. So we created this Persona Toolkit information application that's available at toolkitinfo.opensciencegrid.org. And it points to not only documentation, but various monitoring, applications, user dashboards, analytics that we have available. And our goal is to try and maintain this in the long term to be sort of the central location that users can go to and find out the newest, most relevant information that we know about And so I would encourage everyone to have a look at the page and also give us feedback and suggestions. If we're missing something that would be useful to add, if something doesn't work right, if you have suggestions for improvements, we'd love to hear it. So I guess right now, with the SAND project ending, there's still a lot of work to do. And one of the main areas that SAND laid the groundwork for was really getting us ready to do some detailed machine learning. And we've just submitted a new proposal to the National Science Foundation to try and take what we've done in SAND and build the real machine learning analytics and alerting infrastructure that we want with all of these pieces. There's also work going on with the Research Networking Technical Working Group to augment the network visibility, control, and utilization by focusing on packet marking and flow labeling, traffic shaping and packet pacing, and network orchestration and management. Those are the three main areas that this working group is focused on. And primarily, we've started on the first part, the packet marking and flow labeling. We're trying to make some progress there. That additional information would certainly help us understand how the science flows actually go through the global RNE networks. In addition, there's a WLCG monitoring task force that's trying to get site networking information available. That's really to help us understand where there might be bottlenecks, where there are architecture problems in our global infrastructure. Primarily, we want to start with just getting the real-time in and out from each site individually identified and stored in our monitoring. And lastly, we're also yet again evolving our network pipeline to now leverage the HTTP archivers directly into Elasticsearch. And this is related to the perf sonar developments that are coming out with version 5, where the ESMOND interfaces, or MA, is being replaced with Elasticsearch. And so we're sort of staging to take advantage of that. So to summarize, the SAND project worked in a number of areas to maintain an effective, efficient metric pipeline, to provide an infrastructure to monitor our infrastructure and analyze those metrics and extract new insights from the data that we actually have. So the high-level goal was to extract value for scientists, site, and network administrators from all of the data that we have. And the OSG and WLCG communities are continuing to work together to build on what SAND started. And we certainly welcome your feedback in any areas that might be of interest to you. Please contact us and let us know if you have an interest there. And I will end up stopping there, acknowledging the support we got from the National Science Foundation and our collaborators globally. So thank you.
Thank you, Shawn. Thank you very much for the presentation. As in the previous sessions, we will continue with the next presentation and have questions in the chat or after this session in the Q&A. So our next presenter is Doug from Indiana University. So Doug, can you please share your screen?
All right, will do. Thank you.
Yeah.
So we've had a lot of really good presentations today about some very specific use cases and very deep insight into specific data sets and gathering as much as possible. And so wanted to take a second to talk about NetSage and kind of how this fits into this, analysis framework and this RNE improvement we want to take a look at. So a quick overview of NetSage for people who may not be familiar. NetSage was originally an IRNC project for a few specific links and has grown in that time to include a bunch of different international circuits and domestic here in the US as well. It was a collaboration between IU, LBNL, and the University of Hawaii, and is currently running on a no-cost extension, and there looks like is going to continue well on into the future based on current funding levels. But it was a tool to understand the larger, broader picture of networks. What we were finding in the early stages of NetSage development was kind of a hole in an area where, how do I look at this on a much larger scale and understand who I'm doing data transfers with and what those look like, as opposed to individual transfers or individual small performance problems. Who are we doing a lot of business with, and in terms of networking and data, and what do those transfers look like, and are they performing the way we think they are? So the approach to this was we built NetSage around answering specific questions as opposed to just presenting data saying this is the data we have, come look at it. It was, if I have this data, if I have flow data, if I have SNMP data, what kind of questions would I ask about that? And so the NetSage navigation itself is built around those specific types of questions, and the dashboards were developed around, if I ask this question, what would be the best way to answer it, given the network data that I have? And so again, we're looking to develop human readable summaries and patterns, and not just by network engineers that have really high level insight into the network, but being able to take this data and these insights and put them in the hands of researchers who may not have a high level of network understanding, but can certainly understand performance implications for large transfers. For instance, if I transfer to this facility, it only takes me an hour to transfer this amount of data. But if I go to this other facility, this other partner, now it takes 3 or 4 hours to do the same transfer. Why is that? Now we can start asking questions like that. So these are just some examples from some of the dashboards that I pulled fairly quickly when I prepared this. Up in the upper left corner, SNMP graph. So there's an interesting little pattern there. I see something like that in an SNMP graph, and I'm wondering what it is. And again, it's just a way to present that data and ask a question of, maybe, is that worth looking into? Is this a repeating thing that happens all the time, or is this a one-time type of event? Another question that came up when I was looking through NetSage was this particular one. We're doing transfer. There's a lot of transfers from Singapore to Taiwan, but they are crossing the I-2 link in Los Angeles. Why is that? There's no way that's the most efficient route between those two countries and those two institutions. So let's take a look at that. Let's see what the routing problem is and if there's anything we can do to make that better. Or just in general, if you've got two partners that are doing a fair amount of flows and a fair amount of traffic, why is the average rate so slow? Just being able to see these allows us to ask questions about the network. And really, that's the start of improving any kind of network performance, is understanding what's happening in the first place. So currently, NetSage on the international front looks a lot like this. We have SFlow from those entities, and we have SNMP for all of the ANA links currently. And we're working on adding more and more all the time as we have new partnerships and develop new relationships. And as just the global R&E fabric changes, there's always new links coming up and old ones being retired. So how do you get data into NetSage? Got a couple options. NetSage can ingest flow and SNMP data. The global NOC handles that data ingest, and then all of the data that is ingested is secured, is stored securely in our OmniSoc, which meets the most stringent security measures that are currently out there in the United States. We have HIPAA data stored there. We have federally sensitive or federal data that is sensitive that's stored there. All the NetSage data gets stored there as well. So it's completely secure. It's not just in some random data rack. The other option is we can run a Dockerized version of the ingest pipeline. So we'll talk about the pipeline in a second, but all the stages that happened in that data ingest pipeline can actually be run locally on site in a Docker container. And then you can send us the flows that have already been processed. But regardless of how you choose to do that, NetSage never has the full IP address. So I repeat that a couple different times in this presentation, because one of the questions we almost always get when people look at NetSage data is, that's really interesting. What's the IP that's coming from? Well, we can't tell you that. To maintain data privacy, we never have access to that. So we can never give you that specific level of information. But that keeps us GDPR compliant and makes sure that, various institutions across the globe are willing to share data with us. So we can take SNMP flow. TStat data is a specific instrumentation that we do for DTNs. So we do actually instrument data archives as well. And then we can also ingest per sonar data, so latency, per sonar test, that sort of thing. That all gets collected, goes into the ingest pipeline, where we discard flows that are smaller than 10 megabytes, because typically we're interested in large flow data. And it also helps us keep data anonymity at the top of our list, because now we're getting rid of stuff we don't need to see, like DNS queries and other small things. And we're also typically eliminating a lot of small traffic like email and other things that we don't necessarily need to see in NetSage. We stitch together long duration flows. From NF dump, it's broken up into 5-minute chunks. So if the flow is longer than that, we stitch them all together. We do CAIDA tagging, which is basically GeoIP, trying to match an IP address to some sort of DNS name or resource. We also do science registry tagging, which we'll talk about in a second. And then lastly, we de-identify everything. And then that all gets stored in the NetSage archive, which is a mixture of Elasticsearch and our TSDS database. And then that information gets fed into the performance dashboards that you're going to see. So again, we de-identify everything. We don't anonymize, we de-identify, but everything is tagged and matched before it's de-identified. So we have a reasonable amount of certainty where the flow came from, regardless of the fact that we can't show you the full IP address. And our data privacy policies are out there on the web if anybody wants to take a look at those. So the science registry I just mentioned, that is an effort to match flows to specific resources. And all the data from the science registry actually comes from end users. So you tell us about your network. You tell us that this IP address is actually this specific DTN or this specific scientific instrument or this specific compute cluster. And that information comes from you, gets fed into the science registry. And currently we're matching that by IP. However, we are looking at some different options with the packet marking group down the road to get some more specificity there. And we'll talk about that in a second. But the idea here is we can match resources more specifically than we can with just a generic CAIDA GeoIP tagging or a DNS request where we get a DNS name that may not help us identify that resource. And so this is one of the things that as we develop relationships with end users and with institutions makes NetSage really, really valuable to be able to say, no, we know that this is a specific piece of this instrument and the flows coming from them are related to this specific science domain. So packet marking is an effort that's been born out of the LHC group, and there's a lot of different players across the globe involved in developing a standard for this. It's still pretty nascent, but the first data challenge that happened for LHC, there was already some very rudimentary versions of packet marking that were happening. The reason this is important is as packet marking matures, we can incorporate this data into the science registry. And now, instead of saying this IP address relates to this specific DTN, now we can actually say that this flow is this specific science domain, because one IP address may represent an entire cluster of DTNs or an entire file system or an entire series of scientific instruments. And so with packet marking, as that progresses, now we have the ability to say that these flows are in this specific science domain. And that's going to be really important moving forward, giving NetSage insight into what kind of traffic is flowing while still keeping everything GDPR compliant and keeping everything de-identified. Okay, so back to NetSage. I want to give a quick overview of the kinds of projects that are coming up. We've talked about international NetSage, but there are multiple different applications as we seek additional funding and keep moving forward with the project. So one of the first ones we're looking at is the campus use case. So right now, NetSage is very good at understanding north-south data movement in and out of campuses. But one of the things we're finding is on large campuses, in large scientific endeavors with different facilities, how does data move around a campus is a question that keeps coming up. When you're talking about a research lab, talking to the a specific compute resource or to the data center, what does that look like? And now when we're talking about scientific flows that go from an institution, where are they actually going on campus versus just having kind of the edge of the network instrumented? What do things look like deeper into the campus? And that actually informs north-south data movement as well. For instance, if you have a researcher that is transferring large amounts of data with an archive halfway around the world, if you understand what's happening on the campus level, you can start to understand, are they using a DTN to make that transfer that's been specifically tuned, or are they using a laptop that's connected to wireless? those kinds of questions, a lot of times when we look at performance, we think the network's to blame, but maybe some of the questions become more, what's the endpoint look like, and where are these transfers, where are these flows originating from? And sometimes those simple answers help us develop a better plan for moving data. So campuses are already really, really good at gathering data in general. You go ask your network engineer, they're going to have a lot of data on hand. However, putting this again into a more human readable format that you can pull meaningful patterns out of to look for things that need to be addressed is really, really valuable. Plus, CI personnel, they're busy. Everybody who deals with either systems or networks is on average has more on their plate than they can handle. So trend analysis becomes very, very difficult. NetSage is going to take all this data at the campus level and put it in the hands of stakeholders so that they can look at performance data. And if they think there's a concern, maybe they can start to develop a plan with campus CI personnel to address that. So again, it's taking that data, making it more useful to a larger group. So the NetSage framework for this doesn't need to be really, really heavily modified, but there are some changes. The science registry becomes much more important because you're going to have basically a science registry on your campus that does mapping to every resource on your campus. So that becomes a source of truth. And the other side of this is we're probably not going to be doing de-identification anymore. We're going to keep the full IP address because since this is for your campus, you can have it password protected. You can limit who has access to it. So that de-identification really isn't necessary or desired anymore. So there's some tweaks to the ingest pipeline and how things work. And the types of dashboards that the data is displayed on will probably change a little bit as well. Another one we're looking at is NetSage for a supercomputing facility. So not every campus, not every institution can afford to have their own HPC center. However, with the growth of high bandwidth networks, those types of resources are now accessible by researchers who they don't have that resource locally, but they can now move data to and from an HPC center, maybe across the, across the region or even across the globe. But in terms of what does the entire life cycle of that job look like, that's a hard question to answer. So what we're looking to do is understand who submitted jobs and what the entire job looks like end to end. So from the time it was transferred to the center, how long everything took to process, and then how long it was taken, the results were taken to transfer back. So understanding that entire end-to-end transfer of a job and the entire life cycle of a job is a little bit harder than just understanding where flows are going to and from. And when you add in people working across the globe on one project, all coordinating but using similar resources, it gets a little more challenging. So this one's not quite as straightforward because now what we're looking at is not just mapping flows to resources, we're looking at mapping flows to jobs. So this specific group of flows from this diverse geographic region is all related to this specific HPC job. How do you correlate those? So as we're looking into that, we've had a lot of really, really solid insight from TAC and a couple other supercomputing institutions here in the United States who do a lot of really good record keeping for Globus and other transfer protocols that they use. And now we're figuring out how to correlate that into the giving a picture of the entire job. So we know how long it took to transfer, how long it was in compute, how much data storage it used, all those kinds of things. And you have a whole picture of what an HPC job looks like, including the network use. One of the last ones I want to touch on real quick, we talked about it really briefly earlier, was NetSage for LHC. So LHC is kind of the prime example of the network being part of the instrument because not everybody has a large hadron collider in their backyard. In fact, no one does except for Geneva. So you have data coming in from all over the world, and you have data that's being processed and viewed and analyzed all over the world. And especially with these upcoming LHC, the high luminosity challenges, we're talking about stressing the global R&E fabric to its absolute maximum. In fact, right now, there's not enough bandwidth in the ANA to actually support the HL use case. There will be, but currently there's not. So what we're interested in looking at is, what does that look like on the global scale? What kind of tool could we use to visualize when the network is stressed, what that means in terms of how data or how flows are being distributed across links, and what that does to traffic congestion, and how traffic gets dynamically shifted depending on how busy specific links are. So each particular endpoint has really, really good ability to capture SNMP and flow data. They're storing all those records. And one tool can't possibly answer every question that comes up. So each individual site has all of these different pieces of data that they've collected. But how can you take a look at that? We think that NetSage can be the tool that actually can give you a broad enough view to understand all the trends. And then you can take all that really specific local data that you've collected and answer specific questions. If you can see the whole picture, you can ask questions about the specific. And so that's the idea behind NetSage in this use case, is to allow people to ask those questions and make better use of the local data that they're already collecting.
Time.
So I'm at time, but basically kind of a sum up, packet marking is going to be essential for this entire project for the LHC, and community involvement to get data from endpoints is already starting to happen. We're pulling in some data from CERN, and we have some other players on board that are interested in contributing to NetSage for this specific project. So I will go ahead and drop my share, and we'll go on.
Oh, thank you, Doug. Thank you. So the last presentation is from Andy Lake from ESnet. So it's not the best thing to have the last presentation in the workshop, but I believe that the audience will remain here, and also for the Q&A session.
I thought that meant I was the main event, so kind of let me down. So, so anyways, I think there's been a very good flow to this workshop today, because I think Doug's leads really well into mine. In fact, I was mentioned in his last bullet that was highlighted up on the screen. So Stardust is basically kind of an extension ESnet has done to the NetSage project to handle some of kind of its internal use cases. So, Doug mentioned those people kind of looking at the data and saying, hey, but what's the IP? So ESnet was one of those. So we kind of took the system and built it so it could tell us some of that information and a lot more, as we'll see. So I know we're kind of running late. I don't think to this group I need to make the argument for why we need to measure networks, but I do think kind of one important thing, and I think it's been highlighted here, is that to do a lot of the types of work that's been presented here today, it's ideal to have access to a bunch of different types of network data. So SNMP data, flow data, persona data, et cetera, et cetera. And so, Doug mentioned in NetSage, one way it's often framed as asking questions. Another way we kind of sometimes think about it is the ability to tell stories. And so at ESnet, we want to, and I think most of our organizations, we want to be able to tell different types of stories about our network, right? And so some of that's kind of more kind of down in the details, operational stories and engineering stories, and things like that. There's also some of the higher level stories. We get a lot of questions these days, for example, about, what's traffic look like to countries like Ukraine and Russia and things like that. And so you want to be able to basically provide the context of those measurements and relate them back to the real world in order for them to be effective. And so really kind of getting that contextual metadata is important. And so kind of with all this stuff in mind, and kind of last year and a little bit into the year before, ESnet kind of found itself at, we were collecting a lot of these different data sets. They were kind of dispersed all over the place, in terms of our infrastructure. We had different software collecting them. Sometimes we had repeat sets. It was, different groups were sometimes doing the same thing, or knew certain data sets better than others, right? And so we kind of wanted to bring that together. So we started this team across the groups at ESnet, so software and network engineers, system engineers, people from our security teams, things like that, and kind of all started meeting together to kind of form a more coherent strategy around that. As fate would have it, we actually, in the midst of that, an issue kind of came to light with our current flow collection system. Basically, it was this legacy system that had been end of life for a while, but things were really going to come to a head when we started deploying out the ESnet 6 routers. A few months after that, we basically wouldn't have enough seats to be able to, and the license to collect all that data. So we needed to get something in place, which started this evaluation process where we looked at multiple different solutions. One of them was a NetSage based solutions because our ESnet participated in that project. So we had some familiarity there, but we looked at a bunch of commercial products as well. And, like I said, we had this cross-disciplinary team, and I think there was, a healthy amount of skepticism when we kind of, initially tried to throw NetSage in the mix with all these other products. Is, why would we try and do something developed? We should just buy something off the shelf. But when we actually compared things and looked at what we actually needed, long story short, NetSage kind of came out on top in terms of not only did it have potential for the specific flow case, but it also had potential to bring in some other data sets and do a lot of the correlations that we're talking about. And it's actually really interesting. It's probably a presentation in of itself of just kind of the state of kind of commercial products in this space. A lot of them are very security focused or use case specific focused or vendor focused or things like that, right? So we kind of felt this put us in the best spot. So we were actually able to kind of crank out a solution in a few months. And so we built this service that we call Stardust. And so this is kind of the technical diagram for Stardust. Basically, if you start on the bottom, we have a bunch of collectors, and the collectors can take different forms depending on the data set. So right now, we actually pull in a whole bunch of different or multiple different types of data. So I mentioned flow already. We pull in SNMP data as well. And that includes, a variety of different types of information we get out of SNMP. Power data, your usual interface data, and various forms of that. We also pull in some BGP data, which we primarily use to telegraph or to correlate with the flow data. I'll show an example of that in a moment. We should pull in some optical data out of our optical transponders. And then we have a few experimental data sets, I guess you could call them. One is what we call high touch. So it's kind of packet inspection done in hardware, and then it sends up summaries. And then Doug had mentioned some of the work with the LAC data challenge. Part of that was these things called fireflies, which every time a flow, in addition to the packet marking, another strategy being explored is these fireflies. So every time a flow is sent, it kind of sends this packet to a collector to kind of indicate that this flow started and has some information about the project and things like that. So we collected those and correlated that to flow data. And then we're working on a couple others. Ironically, we actually don't have persona data in there yet. We have it going in the dev cluster. That's actually one of the easier ones to integrate because this is a very similar path. So anyways, we're collecting all these data. It ultimately works its way up to a message bus. It's Kafka in our case. And then it hits Logstash, again, very similar to NetSage, where this metadata correlation happens. So Doug talked about the science registry. We have an internal data kind of customer and inventory database called the SDB, where we can pull in some additional information. Then we store it in Elasticsearch, and we can do things like build Grafana dashboards, which I'll show in a moment. If you've ever been to the my.es.net portal, that's all driven by this data. And then we can also give researchers access to that data via an API to do things like ML or whatever, right? And so the ultimate goal of going through all this process and collecting the data is really to kind of give a nice flexible way to kind of build new visualizations and things like that, right? So it's not always just the kind of raw data format you see there, although that is useful and you can still do that in some context. So don't want to knock that too hard, but it's ultimately to kind of build nice, pretty pictures and not just have like the developers being the ones create those. It's also nice for like our network engineers and other people in the organization to be able to do that. And so Grafana, if you haven't used it, allows some of that to happen. And we've actually really seen that ticked up with our network engineering group in the past few months. They've really kind of started to grasp onto that, which has been good to see. So I talked about some of the latest developments kind of already. So I'm going to jump into a demo here. But it is worth noting, like there are certain visualization pieces right now we're trying to like open source. So As part of the NetSage project, there's one plugin that's already been open source and is officially part of the Grafana plugins that you can download. It's called the Sankey graph. We've got another one called the chord diagram and some other thing. And we're working on a map plugin as well that we're hoping to get there eventually as well. I mentioned some of the experimental data sets. And then, as I mentioned, we've proof sonar data coming soon. And we're going to be grabbing some layer 2 flow records as well here pretty soon. So with that being said, I'd actually like to switch out of my slides and kind of show you some of what we're doing on this correlation front. So this is kind of our internal dashboard right now. This is a page we call the AS Explorer. So what it's doing is looking at the flow data. And you basically select an AS number and it'll tell you a bunch of different stats about it. So there's a traffic graph here up at the top. That's talking kind of about the traffic being sent and received from that AS and some breakdowns down below. So just when you load this by default, it selects Lawrence Berkeley Labs. Probably more relevant to this conference. I can look for GÉANT here if I can move my head out of the way. There we go. And so, now we'll see the traffic going to GÉANT. So you'll see it's actually marked as transit traffic, right? And not kind of directly sent and received from GÉANT. So what that means is we actually correlate the BGP data with the flow traffic, right? So normally in a flow record, you see the source and destination of that. So you can easily say, okay, where did this originate from or where did this ultimately end up? But we want to know in some cases, like, okay, in particular, on its way to the destination, what networks did it cross to get there, which BGP can tell us. We can also figure out kind of in some cases how it got here. We don't like to do reverse lookups in BGP because they're highly inaccurate because of asymmetry and you're looking at exchange points and things like that. But we can actually do some lookups. We know in some cases like the incoming interface is directly connected to GÉANT, for example. So we can figure some of that out. So when you just kind of scroll down, you see the top ASs sending to GÉANT that originate in ESnet. So it's a bunch of the national labs here in the US. Same with the destination. Where I think things get particularly interesting though is when you start looking at the AS paths. In particular, the second one. So basically this is saying traffic comes into ESnet and then it leaves for some destination, and on its way to that destination is it's crossing GÉANT. So we can kind of filter on that and kind of see, right now the top basically AS paths that cross GÉANT the way there. So kind of a big use case for this obviously is peering analysis and things like that. In particular with like commercial peers, things like that. Sometimes we want to make decisions about whether it makes sense to get a direct peering or things like that. So this kind of helps informs those decisions. And then we can get some more breakdowns down here. About like the top AS pairs and things like that. So what organizations are, the ones actually talking to each other and things like that. There's even further breakdowns down here that are kind of collapsed by default that include more of that metadata. So what are the top applications? Some of the kind of data transfer tools and IPv3s, often up there and things like that you kind of expect to see. This unknown, I think, is kind of a good thing to highlight, just as often the case with the metadata is we're always trying to fill in gaps. We use kind of standard ports that we know to categorize things, but they don't capture everything. So we're constantly trying to kind of refine that and fill that in, and whether it be application or anything else. And so then kind of one other thing I wanted to highlight here is, so we've got data like about the interface, right? And so far we've only looked at flow data and some BGP. But let's say we kind of want to drill down into one of these interfaces. So this one on our ESnet CERN router, interface named 2L8C1 GÉANT. Let's click on that. And so this is going to take us to another dashboard, which again up at the top here is flow data. So this is the flow data going across this interface, kind of in and out. We kind of see the standard graphs that we saw here. But correlating across the data sets is kind of an important kind of theme. And so we also have SNMP data. So we have these graphs here where we can actually see the SNMP graphs, which, as you'd expect, they look pretty similar to what we have above. And then if we want to drill down even further and see, all the data we have about this particular interface from SNMP, we can do that as well. Clicking here, again, get your errors and discards, and then we can really get a whole bunch of information about it. So this is a virtual interface on top of a physical interface. So we see that, we can drill down into that. If it was a lag, we can see the lag members and click through to those. Same deal if it was that physical port, we'd get like this interface and anything else on top of it and drill down. And then we have a bunch of stats. So these are Nokia. So some of these are Nokia specific things like SAPs you may or may not be familiar with. It's kind of like how they kind of virtualize sub interfaces and things, I guess is a really probably poor way to describe it. But, we can get per queue stats and things like that here. This is on Q5, which is, I think, is one of our best effort queues and stuff like that. But we can really drill down into the nitty gritty, right? By correlating these things, right? So this is kind of an example of some of the stuff our engineers and operations people can do and kind of dig down into problems. Since I have, I guess, another minute probably, I can really quickly show you some of the work we've done with the Firefly data. So this front page, maybe not super exciting. It's a big table, but basically it lists the Fireflies. It's filtered by some organizations that I happen to know do, some pretty big flows. So we have those sent to us. We collect them. You can see kind of the data in the Firefly here. So it gives us the experiment and the activity and things like that. And if we click through, then we can actually get the net flow data and see kind of the transfer rate and things like that. Now, I think the ultimate goal of these Fireflies is not necessarily to do things like this. It's interesting that we can make that correlation. I think it's ultimately to ask questions and just presumably have lots of networks kind of looking at these and say, hey, did you happen to see this particular flow that we have a Firefly for and things like that. But just kind of, this was some initial work done during the LSE1 data challenge to kind of prove out we could do these types of correlations. So there's a whole lot more I could show you, but I know we're kind of short on time today. I encourage you to go through my slides. I have a few more examples of different things that we've done. And just, kind of to wrap up, right now we're kind of at the stage where we've handled a lot of our internal use cases. We're really kind of at a point where we're kind of looking to share ideas with others. I mean, I see commonalities and like the Brian thing or the Brian project that was talked about earlier using Grafana and kind of some open source database. And I think that's influx based, if I recall correctly. Obviously parallels with NetSage and kind of working with people and figuring out whether we can, what code makes sense to share, what ideas make sense to share and things like that. And yeah, so that's pretty much all I have for today. So I can stop there.
Thank you, Andy, very much. Thank you. This was really, really amazing. At the end, I would like to thank a lot to all the presenters and to apologize that I interrupted some of you and that I bothered you with my emails in the past couple of weeks. Those of you who haven't sent me your presentations, please do that. We would like to make this event page as complete as possible so that later someone can take a look at the presentation. As I said, the video of this whole workshop is going to be published on the GÉANT YouTube site. I would just, before giving you a couple of minutes for discussion, I would just like to share one screen with the upcoming events that we are going to organize. In approximately 1 month from now, there is going to be a second telemetry and data workshop with 3 different themes, sources of telemetry, P4-based telemetry, and data sharing. And this is why I was chatting with Ivana in the background and discussing whether this presentation about NetSage was maybe would maybe be a good fit for that workshop as well. Then in May, we have Campus Network Management as a Service event. There is a SIGNOC, which is going to be in Cambridge this year on 10th and 11th of May. And third European Persona User Workshop, which is going to be, as far as I know, it is planned to be a virtual event, not an in-person event. Ivana, have I missed something? I see that you are sending
yes, I forgot to mention actually that there will be also GNAG meetings. So it is also listed at the events page, but I also put direct links in the chat. So just check it out if it is of interest to you.
Okay, now I would like to invite workshop participants to share your thoughts about the last presentations, the last set of presentations that we've seen, to ask some questions, or to make some comments.
I think one natural question to ask is how there can be more cooperation and collaboration with people from ESnet and the US side in terms of these tools. And we've heard from NetSage the options for getting ingest into NetSage. I don't know whether the same applies to Stardust or whether it's still at a stage where you wouldn't be wanting to do that yet.
Sorry, what was the ask? I was answering some questions.
Sorry, Andy.
No, it's okay. Yeah, so,
yeah.
What was the question for me?
Sorry. So the question is, how there might be collaboration between the NRENs in Europe and ESnet and others in the States in terms of use of these tools. I mean, you've done a certain amount of development and you've clearly demonstrated some useful things there. NetSage has, Doug's explained with NetSage how you can have your data ingested via a container you, I think, run or directly. Is there something similar for Stardust, or is it not at that stage yet?
So no, there's not, and we wouldn't do anything. I think if we did anything on that front, it would be through NetSage. I don't think so obviously there's a very close collaboration there. I don't think we'd want to run a separate pipeline. If there was anything, so we use part of the NetSage pipeline as well. If there's anything useful we develop, we'd probably feed it back into that pipeline as opposed to doing something separate. But we're definitely up for discussions and ideas and how we can share stuff. So
okay, thanks.
I guess I just would have a quick comment here that as an end user, as a WLCG scientist, I'd love to see the ability to have what Stardust provides for more than just ESnet. So I'd like it for GÉANT, RNP, I'd like it for all the global R&E networks. So I guess that relates to Tim's comment about how to collaborate and how to make progress globally. So I don't know if people have good ideas or ways to push forward, but that would be really impressive if we could get that kind of information broadly.
Well, and Andy, I'll kind of spring this on you because I want to talk to you about this anyways, but we're looking at a NetSage instance for supercomputing this year. And I wanted to work with you on possibly integrating some of the stuff you're doing from Stardust, especially the optical data, into that. So there's already some projects on the back burner that are we're still working with supercomputing to iron out some details, but they are very interested. And so some of the stuff you're looking for, Shawn, may come out of some collaborations like that later this year.
Okay, thank you. Do we have any other question or comment? Well, if not, then I think we can end this workshop. At least from my point of view, it was a good one. We had 9 presentations around different topics and a lot of content. I think I will have to re-listen again some of the presentations because there were some very interesting things that were said during the day. Thank you all. As I said, thanks to all the presenters. Thanks to all the participants, and see you at some of the future events, and hopefully we will be able to travel and to meet in person at some of the upcoming events. So thank you very much and have a nice rest of the day.